Imagine walking into a store, and without knowing it, you are part of a secret experiment. Half the customers get one version of the store layout, half get another. Which one makes people buy more? That's the essence of A/B testing, an algorithmic method that decides everything from the color of a button to the headline of an article, and you're always the unwitting participant. On the surface, A/B testing looks simple. Show Group A one option, Group B another, and measure which performs better. But behind the scenes, the math is precise. Statistical models weigh outcomes, adjust probabilities, and declare winners with ruthless efficiency. Companies like Google, Facebook, and Amazon run thousands of these tests at any given time, constantly reshaping your experience without asking permission. The goal? Optimize behavior. If a red buy now button converts 3% more customers than the blue one, the algorithm declares victory, and suddenly millions see red. If a news headline keeps you on the site longer, it spreads, regardless of whether it's more accurate. Small changes compound into massive influence, steering what you read, click, and purchase. And here's the unsettling part. You almost never notice. Every second online, you're both the subject and the data. Your choices are harvested, compared, and fed into equations that decide what stays and what disappears. It feels personal, but it's just probability at scale. A/B testing doesn't care about truth, fairness, or meaning. It only cares about measurable outcomes. In that way, it reflects the cold logic of algorithms themselves. Reduce human complexity into numbers, optimize for the metric, repeat endlessly. And as long as it works, the experiments never stop. What if every link on the internet was secretly casting a vote about what matters most? Imagine opening your browser, typing a question into Google, and getting millions of possible answers. Somehow, in a fraction of a second, the search engine knows which 10 deserve to be on top, as if the entire web had just held an invisible election. But here's the twist. Not all votes are equal. A link from your personal blog isn't the same as a link from Wikipedia or from a government site. Some voices weigh more heavily, shaping the map of knowledge we all depend on. This silent election is powered by an algorithm called PageRank. Back in the late 1990s, when Larry Page and Sergey Brin were still grad students at Stanford, they noticed that the web worked a lot like academia. A scientific paper becomes influential not just because it exists, but because many other respected papers cite it. What if websites could be ranked the same way? A link is a citation, and if important sites link to you, you must be important too. The magic lies in how those votes are counted. It's not just about numbers. If a powerful site like the New York Times points to a small blog, some of its authority flows into that blog. That blog can then pass influence onward when it links elsewhere, creating a living, breathing ecosystem of trust and relevance. Suddenly, the web isn't a chaotic tangle of random pages. It becomes a network where importance ripples outward, like gravity bending the space around it. But there's also a darker side. Because PageRank values age and authority, older sites tend to dominate results. New voices struggle to be heard unless they're amplified by already powerful players. This is why your brand new website won't appear on the first page, no matter how insightful your content might be. The algorithm favors incumbents. Over time, this created a feedback loop. The rich get richer, and the big sites grow even bigger. PageRank doesn't run the internet alone anymore. Modern Google uses hundreds of signals, but its DNA still shapes what you see every single day. Every time you search, you're not just asking a question, you're tapping into the outcome of billions of silent votes, cast by links you'll never notice, quietly deciding what the world thinks is important. What if your search engine wasn't just showing you the most popular results, but was quietly learning who you are, what you want, and how you think? Every time you click on a result, scroll past a link, or linger on a page, you're leaving behind tiny breadcrumbs of preference. And like a patient teacher, the algorithm watches, collects, and adjusts. This is the world of learning to rank, a machine learning approach that powers modern search. Instead of a fixed formula, learning to rank is trained. Engineers feed it thousands, even millions of examples of searches, along with judgments about which results were good and which weren't. The algorithm learns patterns. Maybe shorter pages work better for quick facts, maybe longer ones for deep explanations. It notices your clicks, your hesitations, and your corrections when you retype a query. Each action is a hint, and over time, those hints form a model of relevance. The beauty lies in its flexibility. While PageRank treats all users the same, learning to rank personalizes. Two people searching Jaguar might see different results, one for the animal, one for the car, because the system adapts to context. It's like a mirror that reflects your hidden intentions, sometimes better than you know yourself. But there's a paradox. The more it learns, the more it risks locking you inside a filter bubble. If you keep clicking on one type of content, the algorithm will keep feeding you more of it, narrowing your perspective. What begins as personalization can end as limitation. You're not just choosing, you're being guided, nudged, steered toward a version of reality shaped by code. Learning to rank is invisible, yet everywhere. Each search you make is both a question to the world and a tiny vote that teaches the machine how to answer. In that loop, your behavior training the algorithm, and the algorithm training your behavior, the line between seeker and system quietly dissolves. How does Netflix know what you want to watch before you do? How does Spotify queue up a song you've never heard but instantly love? The answer lies in collaborative filtering, an algorithm built on a simple, almost magical idea. People like you tend to like the same things. Instead of focusing on the content itself, collaborative filtering focuses on the crowd. It builds a massive map of users and their preferences, what they clicked, what they ignored, what they finished. If you and thousands of others gave 5 stars to the same movie, the algorithm assumes your tastes align. So when one of them discovers a new show, that recommendation quietly flows to you. The brilliance is that the machine doesn't need to understand the movie, the music, or the book. It only needs patterns. People who like this also like that. The result feels eerily personal, even though it's just math comparing lists. It's like discovering a secret twin somewhere in the system whose invisible choices are shaping your next binge. But the system has quirks. If the crowd's taste dominates too much, you might never discover the weird, niche content that doesn't fit the mold. It's why recommendation feeds can start to feel repetitive, narrowing instead of expanding your horizons. You get trapped in the comfort zone of your own reflection. Collaborative filtering runs quietly, but its reach is massive. Every playlist, every you might also like suggestion, every rabbit hole you fall into online, each is a ripple of collective behavior. It's not just predicting your future, it's nudging it, pulling you deeper into patterns chosen by millions of strangers whose preferences happen to look a lot like yours. Imagine you're dropped into a pitch black valley with only one goal: find the lowest point. You can't see the whole landscape, only feel the ground under your feet. So you take a step downhill, then another, and another, adjusting with each move. This is gradient descent, the mathematical staircase that powers nearly every modern AI, from image recognition to language models. At its core, gradient descent is an optimization method. Neural networks start off clueless, their predictions random and chaotic. Each time the model makes a mistake, the algorithm calculates the slope of the error, in which direction, and how steeply it should adjust. The model then steps downhill by tweaking its weight slightly. Repeat this process millions of times, and the network gradually settles into a valley where errors are minimized. But here's the catch. The landscape isn't a simple bowl. It's full of ridges, plateaus, and local pits. Sometimes the algorithm finds a good enough valley instead of the absolute best one. Engineers fight this with tricks momentum to push past flat spots, random restarts to escape dead ends. The process looks mechanical, yet it resembles human trial and error, stumbling forward, learning bit by bit. Every breakthrough in AI, from translating languages to generating art, rides on this staircase in the dark. Gradient descent doesn't understand anything. It just follows a blind path of correction. Yet out of that blind path emerges something astonishing. Machines that seem to think because they've fallen into valleys deep enough to mimic intelligence itself. Open your inbox and notice how rarely you see spam compared to the early 2000s. That quiet miracle is thanks to an algorithm that's both shockingly simple and surprisingly effective. Naive Bayes. It works on probabilities, asking, given the words in this email, what's the likelihood it's spam? The naive part comes from its biggest assumption that each word acts independently. Of course, language isn't truly independent. Free means something different when followed by gift versus freedom. But the brilliance of naive Bayes is that it doesn't need linguistic perfection. By multiplying the probabilities of words like lottery, prize, or urgent, the algorithm builds a strong guess about the email's category. It learns from data. If thousands of known spam messages contain winner, that word becomes a red flag. If legitimate emails often include meeting or schedule, those tilt the probability the other way. Over time, the filter becomes sharper, silently scanning every message before it ever reaches you. What's remarkable is how such a simple formula holds its own against more complex AI models. Naive Bayes is fast, lightweight, and interpretable. You can literally trace why it flagged the message. It doesn't need deep networks or massive computation. It just needs statistics stacked in your favor. So the next time you scroll through your clean inbox, remember, there's a naive little algorithm standing guard, quietly guessing and usually guessing right. Picture a forest, dense with thousands of trees. Each one is crooked, imperfect, maybe even fragile. But together, they form something resilient. That's the essence of random forests. An algorithm that turns a crowd of weak decision makers into a single powerful predictor. It starts with decision trees, simple flowcharts that split data step by step. Alone, a single tree is shaky. It might overfit, memorizing noise instead of real patterns. But what if you grew hundreds of trees, each trained on slightly different data, each making slightly different mistakes? When combined, their errors cancel out, and their collective judgment becomes remarkably accurate. This process is called bagging, bootstrap aggregating. By sampling data with randomness, the algorithm ensures diversity in the forest. Each tree votes, and the majority decides. It's democratic intelligence, where no single model dominates, but the ensemble thrives. Random forests revolutionized predictive modeling in the early 2000s. They're fast, robust, and versatile, used for everything from medical diagnosis to credit scoring. Their strength isn't in perfection, but in numbers, echoing the old wisdom. A crowd is wiser than the individual. The metaphor fits beautifully. Alone, a tree bends in the wind. Together, the forest stands tall, a living system stronger than its parts. That quiet collaboration is what makes random forests one of the most trusted tools in machine learning. Imagine teaching a dog a new trick. You don't explain the logic step by step, you reward success and ignore failure. Over time, the dog learns which actions bring treats. Reinforcement learning works the same way. But instead of dogs, it's machines. And instead of tricks, it's everything from beating world champions in chess to teaching robots how to walk. At its core, reinforcement learning is about agents, environment, actions, and rewards. The agent tries something in the environment, a move, a click, a step. If it leads closer to the goal, the agent gets positive feedback. If not, it gets nothing, or even a penalty. Slowly, through trial and error, it learns a policy, a strategy for maximizing long-term reward. What makes this powerful is its generality. The same principle can train a computer to master Atari games, optimize traffic lights in a city, or recommend products in an online store. The algorithm doesn't need explicit instructions. It discovers strategies on its own, but the path is messy. Reinforcement learning agents can get stuck chasing cheap rewards, like a dog that only wants treats and forgets the bigger trick. Engineers fight this with exploration strategies, encouraging the agent to take risks, make mistakes, and learn more robustly. The beauty is that from such simple feedback loops emerges complex behavior that looks almost alive. Machines begin to surprise even their creators, finding strategies no human ever thought of. Reinforcement learning is proof that intelligence can grow from nothing more than curiosity, action, and the steady tug of reward. What if solving problems worked like nature itself? Survival, mutation, adaptation, generations competing until only the fittest survive. That's the principle behind genetic algorithms, computer programs that evolve solutions the way species evolve in the wild. It begins with a population of candidates, possible solutions, often random. Each one is tested against a fitness function, a measure of how good it is. The best survive and combine, exchanging traits like parents passing on genes. Some offspring mutate, introducing fresh variation. Over many generations, the population improves, converging toward an optimal solution. The process mirrors evolution so closely it feels uncanny. Genetic algorithms don't know the right answer. They stumble toward it through variation and selection. And yet, they've solved real-world problems humans couldn't crack with traditional methods. Designing antennas for NASA spacecraft, optimizing factory schedules, even generating art. But evolution is slow and wasteful. Most candidates fail, and progress takes time. Still, in fields where the solution space is vast and unpredictable, genetic algorithms shine. They embrace failure as fuel for discovery. In a way, they remind us that intelligence doesn't always come from planning or logic. Sometimes, it comes from trial, error, and relentless adaptation, the same forces that shaped life itself. Imagine standing in a room with two groups of people scattered around. Your task: draw a line on the floor that perfectly separates them. Easy if they stand apart, harder if they're mixed. Support vector machines take this challenge into mathematics, finding the best boundary between categories in data. The best boundary isn't just any line. It's the one that maximizes the margin, the distance between itself and the nearest points from each group. Think of it as the fairest possible divider, keeping the two sides as far apart as possible. Those closest points, called support vectors, define the boundary. Change them, and the whole decision shifts. SVMs shine in high-dimensional spaces, where separation isn't visual but mathematical. They can even use kernel tricks to project data into new dimensions, making separation possible when it looks impossible in the original space. It's like unfolding a tangled knot into a flat rope you can finally cut. For years, SVMs were state-of-the-art in tasks like handwriting recognition, face detection, and bioinformatics. While deep learning has stolen the spotlight, SVMs remain elegant, interpretable, and surprisingly powerful in smaller datasets. At its heart, an SVM is about boundaries, not just drawing them, but drawing them with precision. It's a reminder that sometimes intelligence lies not in complexity but in the art of separation, finding clarity in chaos. Picture yourself in a maze, searching for the quickest way out. You could wander randomly, but that's slow. You could always follow the right-hand wall, but that might take forever. A search does something smarter. It looks ahead, estimating which path is most promising, and balances two things: what it already costs to get here and what it might cost to finish. That balance is its genius. A calculates the shortest path by combining actual distance traveled with a heuristic, an educated guess of how far remains. On the map, that heuristic might be straight line distance. In a video game, it might be grid steps to the goal. Together, these values guide the search like a compass, pulling it toward the finish without wasting time. This is why your GPS feels almost magical. Every time you type in the address, A or a close cousin is at work. It considers roads, distances, traffic, and then finds the route that gets you there fastest. The algorithm doesn't need to explore every possible path. It prioritizes the ones that look most efficient. But A isn't just for maps. It's used in robotics to plan movement, in logistics to optimize delivery routes, even in puzzle solvers like the Rubik's Cube. Anywhere there's a start, a goal, and possible paths, A can shine. It works because it mimics human intuition. We don't walk every street to find a coffee shop. We look at the map, make an educated guess, and refine as we go. A is our intuition written in code, guiding not just machines, but us every single day. What word is most likely to follow peanut butter? Probably end. And what comes after end? Most often, jelly. That's the essence of a Markov chain. predicting the future based only on the immediate past. It's simple, powerful, and everywhere. Markov chains model sequences, words in a sentence, steps in a walk, states in a system by looking at probabilities of transitions. The rule is memoryless. The next state depends only on the current one, not the full history. That limitation might sound weak, but it makes the math elegant and the predictions surprisingly useful. You've seen them in action without knowing it. Text generators, long before AI went deep, used Markov chains to spit out random but eerily coherent sentences. Weather forecasts use them to model rain patterns. Even board games like Monopoly can be analyzed with Markov chains to reveal which squares you'll most likely land on. The beauty lies in their simplicity. By reducing the world to states and transitions, Markov chains capture the rhythm of systems. They can't grasp long-term structure, but they excel at local flow. And when stacked or extended, they become the foundation of more complex models like hidden Markov models, which power speech recognition and bioinformatics. At heart, a Markov chain is a reminder. Much of life is about patterns. Where you go next often depends only on where you are now. And with enough data, those patterns aren't random, they're predictable. Imagine heating a piece of metal until it glows, then slowly letting it cool. As it cools, atoms settle into a stable, low-energy structure, rush the process, and flaws remain. Do it slowly, and you get strength and order. Simulated annealing borrows this principle from metallurgy to solve optimization problems. The algorithm starts with the random solution and an initial temperature. At high temperature, it accepts not only better solutions but also worse ones, allowing it to jump out of local traps. As the temperature decreases, the algorithm becomes pickier, accepting only improvements. Gradually, it cools into a near-optimal solution. This randomness is its strength. Traditional methods often get stuck in local minima, like a hiker trapped in a small valley thinking it's the lowest point. Simulated annealing allows escapes at first frequently, then rarely until the system finally settles in a deep valley. It's been used in everything from circuit design to airline scheduling. Wherever the search space is too vast for brute force, simulated annealing provides a clever shortcut. What's fascinating is how this method mirrors nature. Stability comes from disorder, order from randomness, structure from chaos. It's not the straightest path, but sometimes wandering while cooling is the only way to find strength. Imagine walking into a party with 100 strangers. No one tells you who belongs to which friend group, but you start noticing patterns. These 5 people talk about sports, those 3 argue about politics, another cluster debates movies. Without anyone labeling them, your brain naturally organizes people into groups. That is clustering, and k-means is one of the simplest yet most powerful ways machines do it. Here's how it works. You choose a number of clusters, k. The algorithm randomly picks k points as centers. Each data point, whether a person, a pixel, or a product, attaches itself to the nearest center. Once everyone is grouped, the centers are recalculated as the average of their members. Then, points reattach to the new nearest center. This repeats until the groups stabilize. The brilliance is in its simplicity. K-means has been used to compress images by grouping similar colors, to segment customers in marketing, to detect anomalies in datasets, and even to analyze genetic data. Anywhere patterns exist without labels, K-means can reveal them. But it isn't perfect. You must choose K beforehand, and the results can change based on the initial random centers. Yet, despite these flaws, it remains a go-to tool because it uncovers hidden structure in messy reality. At its heart, K-means is a digital mirror of how humans see patterns in crowds. We don't need labels to notice similarity, and machines, guided by this algorithm, learn to see the invisible groups that shape the world. Think of a game of 20 questions. Is it an animal? Yes. Does it live in water? No. Does it have fur? Yes. Each answer cuts the possibilities in half until you arrive at the truth. Decision trees use that exact process, but instead of guessing animals, they make predictions from data. A decision tree is built by splitting data based on the most informative questions. For example, if you're classifying fruits, the first split might be, is it citrus? If yes, you branch one way. If no, another. Each split narrows the field until you reach a leaf node that gives the final decision. Orange, apple, banana. The beauty of decision trees lies in their interpretability. Unlike many black box models, you can trace exactly why a tree made its choice. This transparency makes them popular in industries like healthcare and finance, where explanations matter as much as predictions. Yet, decision trees can overfit memorizing training data too closely. That's why ensembles like random forests and gradient-boosted trees exist. They combine many trees for more accurate, stable predictions. Still, the decision tree itself remains iconic, a branching diagram that transforms chaos into structure. Just as humans ask questions to narrow down answers, machines use trees to navigate choices. Simple, visual, and intuitive, decision trees show that sometimes the path to intelligence is nothing more than a series of questions. What if I told you that one of the most effective algorithms in machine learning is also one of the simplest? Naive Bayes, despite its modest name, has power spam filters, sentiment analysis, and even medical diagnosis for decades. Its secret lies in probabilities and a naive assumption. The algorithm is based on Bayes' theorem, the probability of a hypothesis given evidence. For naive Bayes, the hypothesis might be, this email is spam, and the evidence could be words like free, win, or money. The naive assumption that these words appear independently, even though in reality they don't. Surprisingly, this simplification works remarkably well. Each word contributes to the probability score. Enough spammy words push the balance towards spam. Enough neutral words keep it in not spam. By multiplying these probabilities, naive Bayes quickly reaches a conclusion. Its strengths are speed and efficiency. Naive Bayes handles massive datasets with ease, requiring little computation. And while more complex algorithms often dominate headlines, naive Bayes quietly continues to perform, especially when interpretability and speed matter more than absolute precision. It's a reminder that brilliance doesn't always require complexity. Sometimes, making a bold assumption, even an unrealistic one, can lead to solutions that are fast, practical, and surprisingly accurate. In a noisy digital world, naive Bayes remains a clear, probabilistic voice of reason. Imagine standing on the top of a dark mountain with no map. Your goal is simple. Find the lowest valley, the point where the ground is most stable. You can't see far, but you do know one thing: you can feel the slope beneath your feet. So, step by step, you take small moves downhill, always choosing the direction where the slope is steepest. With enough patience, you eventually arrive at a low point. This is gradient descent, the algorithm behind nearly every breakthrough in machine learning. In math terms, the mountain is an error function, a surface describing how wrong a model is. Each point on this landscape represents a different set of parameters. The goal is to minimize the error by adjusting those parameters, and gradient descent is the method to do it. At each step, it calculates the gradient, the direction of steepest increase in error, and moves the opposite way. Repeating this process again and again nudges the system closer to the minimum, but the journey isn't always simple. Sometimes the valley is global, the true lowest point, but often there are many local valleys where the algorithm might get stuck. To overcome this, techniques like momentum, learning rate, scheduling, and stochastic gradient descent were developed. They shake up the process, preventing stagnation and speeding convergence. Without gradient descent, neural networks wouldn't learn, language models wouldn't speak, and image recognition wouldn't function. It is the silent climber that descends the invisible mountains of data, guiding models toward intelligence. What makes it beautiful is its humility. It doesn't leap, it doesn't guess, it doesn't need to see the whole landscape. It simply listens to the slope beneath its feet and trusts that by following it step after step, truth lies waiting in the valley. Imagine teaching a child to throw a ball into a basket. At first, they miss badly, but with each throw, they get feedback. Too far, too short, too left. The child adjusts slightly and tries again. Over time, the throws become precise. This process of feedback and correction is exactly what backpropagation does for neural networks. Backpropagation, or backprop for short, is the algorithm that allows deep learning models to learn from errors. It works hand in hand with gradient descent. First, the network makes a prediction. Then, the error is measured. How far off was it from the correct answer? Backpropagation takes that error and propagates it backward through the network layer by layer, adjusting the weights of each connection according to their contribution to the mistake. This requires calculus, specifically the chain rule to compute gradients efficiently for networks with many layers. Before backprop, training deep networks was almost impossible because the calculations were too slow and unwieldy. With backprop, the process became not only feasible but scalable, unlocking the rise of modern AI. Think of it like blame assignment. If the output is wrong, which neuron was responsible? Backprop spreads the responsibility fairly, tweaking each part just enough so that next time the output is closer to correct. Repeat this millions of times, and the network can learn to recognize cats in photos, translate languages, or even generate music. The genius of backpropagation isn't flashy. It doesn't invent knowledge out of thin air, it refines it slowly, tirelessly, relentlessly. Every mistake is an opportunity, every wrong answer a lesson. Just as a child becomes skilled through repetition and correction, machines gain intelligence one tiny adjustment at a time. Backprop is the teacher, the critic, and the guide that transforms raw networks into systems that understand the world. Imagine looking at a photo. You don't process every pixel at once. First, your brain catches edges, lines, corners, simple shapes. Then, it combines those into textures and parts of objects. Finally, you recognize the whole. A face, a tree, a building. Convolutional neural networks, or CNNs, are designed to mimic this exact process, giving machines the ability to see. At their core, CNNs use filters, also called kernels, that slide across an image. Each filter highlights certain features, edges, curves, color changes by calculating small dot products with the pixels beneath it. The results form feature maps, which represent the presence of specific patterns in different regions of the image. By stacking many layers of filters, the network gradually learns to detect increasingly complex features, building from edges to eyes to entire faces. Pooling layers add another trick. They compress information by summarizing regions, keeping only the most important signals. This reduces complexity while preserving meaning, much like your brain ignores irrelevant details to focus on what matters. By the time the image passes through multiple layers of convolution and pooling, the network has distilled raw pixels into abstract concepts that can be classified with remarkable accuracy. CNNs revolutionize computer vision. They power facial recognition systems, medical image analysis, self-driving car perception, and even art generation. What makes them magical is that they learn their own filters. No human tells them what to look for. Given enough examples, a CNN figures out the right patterns itself. The rise of CNNs marked a turning point in AI. For the first time, machines weren't just crunching numbers, they were seeing. Each convolution is like a machine's glance at reality, building a visual vocabulary pixel by pixel until it can recognize the world in all its complexity. Think about listening to a sentence. The meaning of the last word depends on the ones before it. If someone says, the cat sat on the, your brain expects mat or sofa, not spaceship. Human language, music, and many other signals depend on sequences where context matters. Recurrent neural networks, or RNNs, were one of the first deep learning models designed to handle this kind of temporal dependency. Unlike traditional neural networks, which treat each input independently, RNNs have loops that allow them to pass information from one step to the next. This creates a form of memory. The network doesn't just see the current input, but also remembers what came before. It's as if each word in a sentence is whispered not only to the present, but also to the future. In practice, RNNs excelled at tasks like language modeling, speech recognition, and time series forecasting. They could predict the next word in a sequence, generate text, or recognize spoken commands by processing sound wave patterns over time. However, standard RNNs struggle with long-term dependencies. Information from far earlier in the sequence tended to fade or vanish. To address this, variants like LSTMs, long short-term memory networks, and GRUs, gated recurrent units, were developed. They use special gating mechanisms to decide what information to keep, what to update, and what to forget. This made them far more powerful, enabling translation systems and early chatbots long before transformers took over. RNNs may no longer dominate headlines, but they remain historically important. They were the first deep architectures that allowed machines to read, listen, and predict sequences in a way that felt human. Every autocomplete you use, every early virtual assistant you tried, owes a debt to the looping memory of RNNs. Imagine reading a book. Your eyes don't scan every word with equal weight. Instead, you focus on the key phrases, the ones that reveal meaning, while your brain fills in the rest. This ability to concentrate on what matters is at the heart of the attention mechanism, an idea that reshaped the entire field of machine learning. Before attention, models like RNNs process information sequentially, often forgetting crucial context from earlier in a sentence. Attention changed that. It gave networks a way to look back at all previous words and decide dynamically which ones are most relevant for the current task. When translating a sentence, for example, the model doesn't blindly march forward. It assigns different weights of importance to each word, highlighting the ones that truly matter. Technically, attention works by creating scores between a query, the current position, and all keys past positions. These scores are converted into probabilities, which are then used to weigh the values, the representations of words or tokens. The result is a context vector that captures exactly the right information at the right time. This simple yet profound idea gave rise to the transformer architecture. With attention, translation models became fluid, summarization became coherent, and text generation became powerful. More importantly, attention is not limited to language. It's now used in vision, protein folding, recommendation systems, and beyond. What makes attention magical is that it mirrors human thought. We don't store entire paragraphs in working memory. We highlight what's relevant and ignore the noise. Machines, thanks to attention, finally learn to do the same. It is the spotlight of AI, selective, dynamic, and transformative, illuminating the most important parts of complex data so that meaning can emerge. Picture a library where every book can instantly cross-reference every other book. That's what the transformer architecture does with information. Unlike RNNs, which trudge through sequences step by step, transformers look at all tokens at once, using attention to weigh their relationships. This parallelism makes them astonishingly powerful and scalable. At the core of transformers is self-attention. Every word in a sentence evaluates every other word, building a map of relationships. For example, in the phrase, "the cat sat on the mat," the word cat is more connected to sat than to mat. By computing these relationships simultaneously across the sequence, transformers can capture meaning with unprecedented accuracy. The architecture is built from encoder and decoder stacks, each with multiple layers of attention and feed-forward networks. Position encodings give the model a sense of order, solving the problem of sequence without needing recurrence. Because all words are processed in parallel, transformers can be trained on massive datasets far faster than RNNs. Introduced in 2017 with the paper "Attention is All You Need," transformers sparked the current AI revolution. They power large language models, advanced translation systems, image captioning tools, and multimodal AI that can understand both pictures and words. Their scalability is what enabled models with billions and now trillions of parameters. Transformers are more than just an algorithm. They represent a paradigm shift from sequential processing to global context, from memory bottlenecks to vast relational understanding. They turn the dream of general-purpose AI from fantasy into engineering. If attention is the spark, transformers are the engine, and together they define the present era of artificial intelligence. Imagine two artists locked in a competition. One tries to forge paintings so convincing that no one can tell they're fake. The other inspects each canvas, determined to expose flaws. With every round, both artists improve. The forger learns to mimic reality better, while the inspector sharpens their eye for detail. This duel never ends, and out of it comes art that could fool even experts. That's the core idea behind generative adversarial networks, or GANs, proposed by Ian Goodfellow in 2014. GANs pit two neural networks against each other, the generator and the discriminator. The generator's job is to create synthetic data, images, music, or text that resembles the real thing. The discriminator's job is to distinguish real from fake. Each time the generator fools the discriminator, it wins a small victory. Each time the discriminator catches a fake, it forces the generator to improve. This adversarial process leads to astonishing results. GANs can produce photorealistic faces of people who don't exist, generate paintings in the style of long-dead masters, or even simulate voices. Their creations are so convincing that they've raised ethical debates about misinformation, copyright, and deepfakes. Technically, GANs rely on backpropagation. The generator adjusts its weights based on the discriminator's feedback, constantly refining its output. Over time, the two networks push each other toward perfection. Like rivals locked in an endless cycle of improvement, GANs open the door to a new kind of AI, creative AI. For the first time, machines weren't just analyzing or predicting, they were inventing. And while the duel between generator and discriminator is purely mathematical, its echoes feel deeply human. Art born from conflict, beauty shaped by rivalry. Think of how a child learns to walk. They wobble, stumble, fall, and then try again. Each successful step is rewarded by cheers, by candy, or simply by the joy of progress. Slowly, through trial and error, balance emerges. Reinforcement learning, or RL, captures this process mathematically, giving machines a way to learn through interaction with their environment. In RL, an agent exists inside an environment. It observes the state, takes an action, and receives a reward, or punishment. Over time, the agent tries to maximize cumulative rewards by improving its strategy, called a policy. Unlike supervised learning, where models learn from labeled examples, RL is more like life itself, messy, uncertain, and full of exploration. One of RL's core challenges is balancing exploration versus exploitation. Should the agent try a new action that might lead to higher rewards, or stick with what already works? This tension makes RL incredibly dynamic. It mirrors human decision-making whether to try a new restaurant or return to the familiar favorite. Breakthroughs in RL have been dramatic. AlphaGo used it to defeat world champions in the ancient game of Go, mastering strategies beyond human intuition. Robotics labs use RL to teach machines to grasp objects, walk, and even fly. In finance, logistics, and resource management, RL optimized choices in complex, uncertain environments. The beauty of reinforcement learning lies in its simplicity. It distills learning into action, feedback, and adaptation, the same loop that governs evolution and human growth. Every time an AI agent wins a game, balances a robot, or improves a recommendation, it's echoing the most ancient teacher of all, experience. Imagine teaching a child to throw darts. Each time they miss, you don't just say wrong, you point out how far left or right they were, how much force they used, and what to adjust next. Slowly, with feedback, their throws improve. Neural networks learn in a similar way, and the process that makes it possible is called backpropagation. At its core, backpropagation is about correcting mistakes. When the neural network makes a prediction, say, classifying an image, and gets it wrong, a loss function measures the error. Backpropagation then distributes this error backward through the layers of the network, adjusting the weights of each neuron so that the model is slightly more accurate the next time. The magic lies in calculus. Using the chain rule, backprop calculates gradients, tiny slopes that show how much each parameter contributed to the error. These gradients tell the optimizer which direction to nudge the weights to reduce future mistakes. Layer by layer, the network improves, learning patterns too subtle for humans to program manually. Without backpropagation, deep learning as we know it wouldn't exist. It allows networks with millions of parameters to train efficiently, turning raw data into refined intelligence. From image recognition to speech synthesis, from recommendation systems to autonomous vehicles, backprop is the silent heartbeat driving progress. It's not glamorous, it's math. But backpropagation transformed neural networks from clumsy experiments into powerful engines of pattern recognition. Every smart app you use, every AI breakthrough you read about, owes a debt to this quiet algorithm that whispers, "You were wrong, here's how to be less wrong next time." Picture yourself lost in a foggy mountain range, trying to reach the lowest valley. You can't see the full landscape, but you can feel the slope beneath your feet. So you take a cautious step downhill, then another, always moving toward lower ground. Step by step, you descend. That's the essence of gradient descent, the optimization algorithm that powers machine learning. When a model makes a wrong prediction, the error is measured by a loss function. Gradient descent is the method of reducing that error. By computing the gradient, the direction of steepest increase, the algorithm takes a step in the opposite direction toward the valley of minimum error. The size of each step is controlled by the learning rate. Too small, and progress is painfully slow. Too large, and you risk overshooting the valley entirely. There are variations. Stochastic gradient descent samples one data point at a time for efficiency, while batch gradient descent uses larger chunks of data. Momentum methods push the steps faster, like a ball rolling downhill, while adaptive algorithms adjust learning rates dynamically. This simple yet profound idea underlies almost every modern neural network. Whether training a chatbot, recognizing faces, or predicting weather, gradient descent is the quiet guide steering weights toward optimal solutions. It's deceptively humble, just a method of taking steps downhill. Yet combined with backpropagation, it gave machines the ability to learn complex patterns from oceans of data. Every leap in AI rests on this steady march through the fog, guided by gradients, always moving toward clarity. Imagine taking a high-resolution photograph and squeezing it into a tiny thumbnail. The details vanish, but somehow enough information remains so that when expanded again, the picture is still recognizable. That's what autoencoders do, not with images alone, but with any kind of data. They compress information into its essence and then reconstruct it. An autoencoder consists of two parts, the encoder and the decoder. The encoder takes the inputted image, sound, or text and compresses it into a latent representation, a small vector of numbers that captures the most important features. The decoder then tries to rebuild the original input from that compressed code. If the reconstruction is close enough, the autoencoder has learned a useful internal map of the data. This process is powerful because it reveals hidden structure. By forcing data into a bottleneck, the network must decide what truly matters: edges and shapes in the image, tones in music, or patterns in language. The less important noise is discarded. Over time, autoencoders learn compact, meaningful representations that can be used for denoising, anomaly detection, or dimensionality reduction. Variants like variational autoencoders go further, sampling from distributions to generate entirely new data that looks convincingly real. Others are used in recommendation systems, medical imaging, and cybersecurity, where compressed patterns help detect fraud or rare diseases. Autoencoders are a reminder that learning isn't only about prediction, it's also about distillation. By stripping information down to its core and then rebuilding it, these models mimic one of the brain's deepest skills: summarizing reality in a way that is smaller, cleaner, and still astonishingly accurate. Think about how words live in your mind. The word king brings with it queen, royal, castle. The word coffee recalls cup, morning, caffeine. Our brains arrange words not in isolation but as clouds of meaning, clustered by association. Word2Vec, introduced by Google researchers in 2013, gave machines the ability to do the same. The idea is simple but revolutionary. Word2Vec trains a shallow neural network on massive text corpora, asking it to predict surrounding words from a target word or vice versa. In doing so, it learns embeddings, vector representations where each word is a point in space. The magic is that geometry encodes meaning. In this space, similar words are close together, while different ones are far apart. Even more astonishing are the analogies. In Word2Vec space, the vector for king minus man plus woman points directly to queen, Paris minus France plus Italy leads to Rome. The model discovers relationships humans never explicitly told it about, simply by reading vast amounts of text. These embeddings transformed natural language processing. They became the foundation for translation, sentiment analysis, search engines, and recommendation systems. They also inspired deeper models like GloVe, FastText, and the contextual embeddings used in transformers. What Word2Vec showed is that meaning can be mapped. Language, once considered uniquely human and ungraspable by machines, turned out to have a structure that mathematics could capture. With nothing more than co-occurrence patterns, a machine could learn not only words, but relationships, analogies, and subtle shades of context. Imagine reading a book. You don't give every single word equal weight. Instead, your eyes skim, pausing on the most important phrases. You remember characters' names, key events, emotional cues. This selective focus is what makes reading efficient. Neural networks once lacked this ability, treating all input as equally important. That changed with attention mechanisms, which let machines decide what matters most. Introduced in 2014 for machine translation, attention allows models to look back at an entire sequence of input and assign weights to different parts. For example, when translating the French sentence "Le chat dort sur le canapé" into English, the model knows that chat corresponds to cat and canapé to sofa, even if the words aren't in the same order. Attention creates soft alignments, helping the network focus on the right context for each output. The mechanism works through weight matrices. Each input word is scored relative to others, producing attention scores. These scores amplify or diminish certain signals, letting the model highlight key features while ignoring noise. Instead of compressing everything into one fixed vector, attention distributes relevance dynamically across a sequence. This seemingly small shift revolutionized AI. It became the backbone of the transformer architecture and, ultimately, large language models. Beyond text, attention is used in image recognition to highlight objects, speech processing to focus on intonation, and even protein folding to track relationships across amino acids. What makes attention so powerful is its resemblance to human cognition. Just as we decide where to look, what to hear, or which thought to pursue, machines now have a way to prioritize. It's a bridge between brute force computation and selective understanding, the spark that transformed pattern recognition into something closer to thought. In 2017, a paper titled "Attention is All You Need" reshaped the AI world. Its claim was bold: forget recurrent and convolutional networks, forget complicated memory tricks. With attention alone, you could build models that scale, learn faster, and understand language better than anything before. These models were called transformers, and they became the foundation of modern AI. A transformer is built from layers of self-attention and feed-forward networks. Self-attention means that every word in a sentence looks at every other word, building rich webs of context. Instead of processing sequences step by step, as RNNs did, transformers analyze them all at once, making training vastly more efficient on modern hardware. The architecture also includes positional encoding, which helps the model remember order, and multi-head attention, which lets it view input from multiple perspectives simultaneously. Combined with layer normalization and residual connections, these tricks give transformers stability and depth. The results were staggering. Models like BERT, GPT, and T5, all based on transformers, achieved state-of-the-art performance across tasks: translation, summarization, question answering, even creative writing. Scaling them up unlocked emergent abilities, reasoning, analogy, and problem-solving skills that weren't explicitly programmed. Beyond language, transformers have invaded other fields: computer vision, biology, audio, and robotics. AlphaFold used a transformer-like model to predict protein structures, solving a 50-year scientific challenge. Transformers didn't just improve AI, they redefined it. They showed that, with the right architecture, scale unlocks intelligence. Today, every major breakthrough in generative AI traces its lineage back to that simple declaration: attention is all you need. Picture a child learning to ride a bike. At first, they wobble, fall, scrape their knees, but with every attempt, they learn, balance longer, pedal smoother, steer straighter. Over time, the crashes lessen, the successes grow. This process of trial, error, and reward mirrors how reinforcement learning teaches machines. In RL, an agent interacts with an environment. At each step, it takes an action, receives feedback in the form of rewards or penalties, and updates its strategy, its policy for the future. Over thousands or millions of trials, the agent learns which sequences of actions maximize long-term rewards. The framework has three key parts: states, the environment's condition; actions, choices the agent makes; and rewards, signals guiding behavior. By exploring and exploiting, the agent discovers strategies that will be impossible to pre-program explicitly. The math often involves Markov decision processes, Q values, and the policy gradients. But at its heart, RL is about learning from experience. Its applications are remarkable. Reinforcement learning enabled AlphaGo to defeat the world's best human Go players, a feat once thought decades away. It powers robotics, where machines learn to walk, grasp, or fly through repeated practice. It's used in recommendation, engines, resource management, and even chip design. What makes RL fascinating is how close it feels to human learning. No fixed dataset, no teacher giving correct answers, just actions, consequences, and gradual mastery. It's intelligence emerging from struggle, one reward signal at a time. And as algorithms grow more powerful, RL brings machines closer to developing strategies that look less like code and more like intuition. Imagine playing a video game where you don't know the rules. At first, you try random buttons, jump here, move there. Some actions bring points, others cause you to lose. Over time, you build a mental table. Pressing this button in this situation tends to work. Q-learning formalizes that process for machines. Q-learning is a reinforcement learning algorithm that learns the value of actions in given states. The Q stands for quality, representing how good a particular action is. Initially, the agent knows nothing. It explores, tries moves, collects rewards. For every action taken in a state, it updates a Q table with a simple rule: current value plus learning rate times the difference between actual reward and expected value. Over time, the table converges toward the true value of actions. This method is powerful because it doesn't require a model of the environment. The agent doesn't need to know the rules beforehand, it figures them out by interacting. As the Q table fills in, the agent starts choosing actions that maximize cumulative reward, effectively learning an optimal policy. Though Q-learning struggles with very large state spaces, it's a foundation for more advanced methods like deep Q networks, where deep neural nets approximate the Q values. These methods trained agents to play Atari games directly from pixels, achieving superhuman scores. At its core, Q-learning captures the simplicity of learning by doing. Try something, measure its outcome, adjust your expectations, repeat. From games to robotics to optimization problems, this algorithm turns trial and error into structured mastery step by step, action by action. What if a computer could dream? Not just replay data it has seen, but invent new faces, landscapes, and artworks that never existed before. That's the magic of generative adversarial networks, or GANs. Introduced in 2014 by Ian Goodfellow, GANs unleashed a new era of machine creativity by teaching machines to compete with themselves. A GAN has two parts: the generator and the discriminator. The generator tries to create fake data, say, an image of a human face. The discriminator judges whether the image is real or fake. At first, the generator produces blurry nonsense, and the discriminator easily calls it out. But with every round, the generator improves, crafting ever more convincing fakes, while the discriminator sharpens its ability to detect flaws. This adversarial dance continues until the generator produces images so realistic that even humans can tell them apart. The results are staggering. GANs have produced photorealistic portraits of non-existent people, designed fashion, generated paintings in the style of Van Gogh, and even helped in scientific research by creating synthetic data for rare diseases. At the same time, they've raised ethical concerns, powering deepfakes that blur the line between truth and fabrication. What makes GANs so fascinating is the principle behind them: progress through conflict. Two networks locked in a struggle push each other to higher levels of skill. Out of this digital rivalry emerges creativity machines not just analyzing reality, but imagining beyond it. GANs showed us that artificial intelligence isn't limited to recognition or prediction. With the right setup, it can invent. And that realization opened the door to a world where the boundary between real and artificial grows ever thinner. Imagine starting with a blank canvas filled with static, like the snow on an old television screen. From that chaos, an image slowly emerges: a face, a cat, a futuristic city. This is the essence of diffusion models, the technology behind tools like DALL-E 2 and Stable Diffusion. The idea is deceptively simple. A diffusion model takes real data, like photos, and gradually corrupts them with noise until they are indistinguishable from randomness. Then it learns the reverse process, how to take pure noise and step by step denoise it into something meaningful. Each step is tiny, but across hundreds or thousands of iterations, the chaos resolves into coherent images. What makes diffusion so powerful is control. By guiding the denoising process with text prompts, a cat wearing a suit, a city floating in the clouds, the model can generate images that match human imagination with uncanny precision. Unlike GANs, which struggle with stability, diffusion models are more reliable and produce higher quality, diverse results. Their applications go far beyond art. They're being explored for drug discovery, where molecules are generated from noisy beginnings into viable compounds. They're used in physics simulations, audio generation, and even solving inverse problems where data is incomplete. Diffusion models capture something deeply human: creativity emerging from randomness. They show us that noise isn't just disorder, it's raw potential, waiting to be sculpted into form. And in the hands of these algorithms, the boundary between static and masterpiece is just a matter of guidance and time. How do you teach a machine to recognize a cat? You show it thousands of pictures, but that's only half the story. The real magic happens in the algorithm that tells the network how wrong it was and how to improve. That algorithm is backpropagation, the heartbeat of modern deep learning. At its core, a neural network is a stack of layers, each filled with weights, numbers that transform input into output. But the weights don't start out smart, they're random. Training means adjusting them until the network produces the right answers. Backpropagation makes this possible. The process begins with a forward pass. The network makes a prediction. Then comes the loss function, which measures the gap between prediction and reality. Backpropagation computes the gradient of this loss with respect to every weight using the chain rule of calculus. This tells the network not just that it was wrong, but how to tweak each weight to get closer to the truth. The adjustments happen via gradient descent. Each weight shifts a little in the direction that reduces error. Over millions of examples, these tiny shifts accumulate into powerful pattern recognition. Backpropagation isn't glamorous, it's math, derivatives, and bookkeeping, but it's what unlocked the explosion of deep learning in the 2010s. Without it, neural nets would remain clumsy toys. With it, they became engines of perception, able to see, hear, and understand. Think of it like learning from mistakes. Every time you slip on ice, you subtly adjust your balance for next time. Backpropagation gives machines that same feedback loop, allowing them to refine themselves into intelligence. Imagine standing on a dark mountainside, surrounded by peaks and valleys. Your goal is to reach the lowest point. You can't see the whole landscape. You only feel the slope beneath your feet. Each step you take is downhill, guided by the gradient. Eventually, if you step carefully, you'll reach the bottom. This metaphor describes gradient descent, the optimization algorithm that powers nearly all of machine learning. In math terms, gradient descent minimizes a loss function by iteratively adjusting parameters. The gradient is the vector of partial derivatives that points uphill the direction of greatest increase. By moving in the opposite direction, step by step, the algorithm reduces error. There are variations. Batch gradient descent uses the entire dataset for each step, while stochastic gradient descent uses one example at a time, introducing randomness that often helps escape shallow minima. Mini-batch strikes a balance, updating with small groups of data. Learning rates control step size, too big, and it overshoot, too small, and training crawls. Gradient descent is deceptively simple. yet incredibly powerful. It turns the intractable problem of tuning millions of parameters into a systematic march toward better performance. It's how models learn to translate languages, recognize images, and play games. In essence, gradient descent is a compass of machine learning, always pointing toward less error. It doesn't guarantee perfection. Sometimes you end in a local minimum rather than the absolute best. But with the right tricks, it brings order out of complexity. Without it, the towering architectures of AI would remain untrainable abstractions. Think of a library where every book can instantly cross-reference every other book. Instead of reading page by page, connections appear everywhere at once. This is the essence of the transformer architecture, introduced in 2017, which became the foundation for today's large language models. Before transformers, recurrent and convolutional networks dominated sequence processing. They worked but struggled with long-range dependencies. Transformers solve this by using attention, a mechanism that lets the model weigh the importance of every word in a sequence relative to every other word. Instead of crawling step by step, it sees relationships globally. The building block is self-attention. Each word is projected into queries, keys, and values. By comparing queries and keys, the model decides how much attention each word deserves, then builds new representations from weighted combinations of values. Multiple attention heads capture different aspects of meaning, from syntax to context. This architecture scales. Stacked layers of attention and feed-forward networks allow transformers to process vast amounts of data in parallel, making training efficient. Models like BERT, GPT, and T5 all share this DNA. The results are astonishing. Coherent text generation, nuanced translation, code writing, even music composition. Transformers aren't just language tools. They've spread into vision, audio, protein folding, and beyond. Their universality comes from their ability to model relationships in any kind of sequence or structure. The brilliance of transformers is how simple the idea seems. Pay attention to what matters, ignore the rest. Yet, that principle reshaped AI. They're not just architectures, they're the engines behind machines that now converse, reason, and imagine alongside us. Picture reading a sentence. The cat sat on the mat. To understand it, your brain doesn't treat every word equally. Cat and mat carry more weight than the. Your mind highlights them, focusing energy where meaning lies. The attention mechanism in AI mirrors this selective focus, and it changed everything. In traditional models, information passed sequentially, often losing context over distance. Attention disrupted that by letting the model assign scores to each part of the input relative to others. A word doesn't just depend on its neighbors, it can directly connect to distant words, preserving context. Mathematically, attention works through queries, keys, and values. Each word vector becomes all three. A query from one word measures similarity against the keys of all others, producing weights. These weights determine how much of each value contributes to the output. The result? A context-aware representation that understands relationships globally, not just locally. The impact is massive. In translation, attention allows the model to align words across languages fluidly. In summarization, it pinpoints the core sentences. In speech recognition, it highlights relevant sounds. By assigning focus, attention makes models not just accurate but interpretable. Attention mechanisms evolved into self-attention, powering the transformer revolution. But even outside that architecture, attention remains a guiding principle. Learn not by treating everything equally, but by emphasizing what matters most. It's an idea both intuitive and profound. Just as humans can't attend to every detail in the world, machines learn better when they, too, know where to look. Imagine teaching a dog to sit. You don't explain the physics of joints or balance. You simply give a treat when it does the right thing. Over time, the dog learns through trial and error, guided by reward. Reinforcement learning is built on this principle, but instead of pets, the learners are algorithms. In RL, an agent interacts with an environment, it takes actions, observes results, and receives rewards or penalties. The agent's goal is to maximize cumulative reward over time. Unlike supervised learning, where the correct answer is always provided, RL thrives on uncertainty. It learns strategies, not labels. The formal framework is a Markov decision process: states, actions, rewards, and transitions. Through repeated episodes, the agent estimates which actions lead to the highest long-term payoff. Techniques like Q-learning approximate the value of action state pairs, while policy gradients directly adjust behavior. Reinforcement learning shines in dynamic tasks. It has trained robots to walk, software to play Atari games, and agents like AlphaGo to defeat world champions in Go, a game once thought too complex for machines. In each case, the agent learns strategies no human explicitly programmed. But RL is also notoriously challenging. Sparse rewards, huge state spaces, and unstable training make progress difficult. Yet its promise is profound. Systems that don't just memorize but adapt, experiment, and discover. Reinforcement learning isn't about perfection. It's about learning from mistakes, over and over, until success emerges. In that sense, it mirrors life itself, where every choice nudges us along an unseen path shaped by trial, error, and the pursuit of reward. Suppose you're in a maze. At each intersection, you can move left or right. Some paths lead to treasure, others to dead ends. Over many runs, you start to remember turning left here usually pays off. That memory is the essence of Q-learning, one of the most influential algorithms in reinforcement learning. Q-learning centers on a Q table, which stores values for every state action pair. Each entry answers the question: if I take this action in this situation, what long-term reward can I expect? Initially, the table is filled with guesses. As the agent explores, it updates values using the Bellman equation. Today's estimate is adjusted based on the immediate reward plus the discounted value of future states. This updating process balances exploration and exploitation. Sometimes, the agent chooses random actions to discover new paths. Other times, it exploits the best-known option. Over time, the table converges toward optimal strategies. One beauty of Q-learning is that it's model-free. The agent doesn't need to know the environment's dynamics ahead of time. It simply learns by experience. Though Q-tables work best in small problems, their principles extend into deep Q networks, is where neural nets approximate values in complex spaces like video games. Q-learning is simple yet powerful. It embodies the idea that learning isn't about knowing everything from the start, it's about storing and updating experiences until patterns emerge. Each action becomes a lesson, and each lesson nudges the agent closer to mastery. Imagine flipping through TV channels. What comes next doesn't depend on the entire history of your viewing, only on the channel you're on now. That's the essence of a Markov chain, a system where the future depends only on the present, not the past. This memorylessness makes Markov chains both simple and surprisingly powerful. Formally, a Markov chain is a sequence of states with transition probabilities. Each state has a fixed chance of leading to another. For example, consider weather. If today is sunny, there might be a 70% chance tomorrow is sunny and 30% chance cloudy. After many steps, these probabilities stabilize, creating a stationary distribution. Though basic, Markov chains underpin huge swaths of technology. Speech recognition uses them to model phoneme sequences. Text prediction relies on them to generate plausible word patterns. They're central in finance, biology, and even board games, where dice rolls create probabilistic transitions. One of their greatest strengths is simplicity. By ignoring deep history, Markov chains become tractable and analyzable. Yet this simplicity doesn't limit them. They're building blocks for complex algorithms like hidden Markov models, where states are hidden but transitions still follow Markovian rules. Markov chains remind us that prediction doesn't always require full memory. Sometimes, the present moment contains enough information to chart the future. This abstraction, born in early 20th century mathematics, now guides AI systems that model language, behavior, and even human decision-making. The world may not truly be memoryless, but assuming it is often makes problems solvable and surprisingly accurate. Suppose you're listening to someone speak a language you don't know. You can't see the grammar directly, but you hear patterns, syllables, pauses, rhythms. Beneath the surface lies a hidden structure guiding the words. Hidden Markov models capture exactly this idea. Systems where you observe outcomes, but the states producing them remain hidden. In the HMM, there are two layers: hidden states that follow Markov chain, and observations that depend probabilistically on those states. For example, imagine weather again. The true state might be rainy or sunny, but you only see someone's choice of clothing. By analyzing the clothing sequence, you infer the hidden weather state. Training an HMM involves two classic algorithms. The forward-backward algorithm computes probabilities efficiently, while the Baum-Welch algorithm estimates parameters from data. Once trained, HMMs can decode sequences guessing the most likely hidden state path behind observed events. HMMs were once the backbone of speech recognition, powering systems that mapped sound waves to phonemes. They remain essential in bioinformatics, used to model DNA sequences, and in finance, where they uncover hidden market regimes. Their beauty lies in handling uncertainty. Life often gives us observations without direct access to causes. HMMs let us reason backward, finding structure beneath noise. Even though deep learning has surpassed them in many domains, the elegance and interpretability of HMMs keep them relevant. Hidden Markov models embody a key idea. Reality often hides behind layers of probability, and with the right math, we can uncover the unseen. Imagine planning a road trip. At each intersection, you must decide turn left, right, or keep going. The best choice depends not just on the immediate scenery, but also on what lies ahead: gas stations, hotels, or dead ends. The Bellman equation captures this principle mathematically, making it the backbone of reinforcement learning. The Bellman equation expresses the value of a state as the immediate reward plus the expected value of the next state, discounted by time. In other words, today's decision balances the payoff you get now with the payoff you'll get in the future. This recursive relationship makes complex planning problems solvable piece by piece. In practice, it underlies algorithms like dynamic programming, Q-learning, and value iteration. By repeatedly applying the Bellman update, an agent refines its estimate of how good each action is, eventually converging on optimal policies. The elegance is in the recursion. Break the future into smaller steps, and suddenly an infinite horizon becomes manageable. The equation is named after Richard Bellman, who developed it in the 1950s as part of dynamic programming. His insight was simple yet transformative. Complex, sequential decisions can be solved by decomposing them into smaller subproblems, each relying on the next. Without the Bellman equation, much of modern reinforcement learning would crumble. It formalizes the idea that the future matters, but you don't need to predict it all at once. You just need to understand how today's choice links to tomorrow's. The Bellman equation isn't just math. It's a philosophy of decision-making. Progress is built not by seeing the entire path, but by trusting that each step forward connects meaningfully to the next. Picture playing chess against yourself in your mind. You imagine one move, then another, exploring different branches of possibility. Some paths lead to victory, others to disaster. Monte Carlo tree search MCTS formalizes this mental simulation, combining randomness and strategy to make powerful decisions in complex games. MCTS builds a search tree by simulating many random games from a position. Each simulation, or rollout, produces an outcome win or loss that updates statistics for the moves leading there. Over time, the tree grows unevenly, focusing exploration on promising branches while still sampling less certain ones. The algorithm follows 4 steps: selection, choose a promising node; expansion, add a new move; simulation, play out randomly; and backpropagation, update results. This balance of exploration and exploitation makes MCTS effective without requiring exhaustive search. Its breakthrough moment came with AlphaGo, the AI that defeated human champions in Go. By combining MCTS with deep neural networks, AlphaGo could evaluate positions and simulate millions of potential games, uncovering strategies beyond human intuition. MCTS isn't limited to board games. It's applied in robotics, planning, and resource allocation anywhere decisions branch into vast possibilities. Its strength lies in its adaptability. The more simulations it runs, the smarter its choices become. At its heart, MCTS shows the power of imagination. By playing out futures in miniature, even imperfectly, algorithms can make choices that seem almost prophetic. Its trial and error scale to a superhuman level, revealing how foresight can emerge from randomness. Imagine trying to climb a mountain. The peak feels impossibly far, but if you break the climb into smaller segments, just reach the next ledge, then the next you make steady progress. Dynamic programming applies the same principle to complex problems. Break them into overlapping subproblems, solve each once, and reuse those solutions to build toward the final answer. The core idea is memoization storing results so they don't need to be recomputed. Instead of brute forcing every possibility, DP creates efficiency by avoiding redundant work. A famous example is the Fibonacci sequence. A naive recursive solution recalculates the same numbers endlessly, but DP stores them once, reducing exponential time to linear. DP shines in optimization. Problems like shortest paths, resource allocation, scheduling, and sequence alignment all rely on it. Algorithms like Dijkstra's and the Viterbi algorithm are DP in action. The method is especially powerful in reinforcement learning, where value iteration and policy iteration rely on Bellman updates, essentially dynamic programming with probabilities. Its strength lies in structure. By carefully defining states and transitions, DP transforms an overwhelming challenge into manageable steps. Richard Bellman, who coined the term in the 1950s, saw it as a way to bring order to chaos through recursion and reuse. Dynamic programming teaches us that efficiency often comes from rethinking, not working harder. By solving small pieces and building upward, problems that once seemed unsolvable become tractable. It's not about brute force, it's about smart reuse of knowledge. In life, as in algorithms, the biggest goals are often achieved by breaking them into steps and never solving the same problem twice. Imagine nature as an endless problem solver. Species survive not because they're perfect, but because the fittest traits endure. Genetic algorithms harness this evolutionary wisdom for computation, using selection, mutation, and crossover to evolve solutions to difficult problems. A genetic algorithm begins with a population of candidate solutions, often represented as strings of numbers or bits. Each candidate is evaluated with a fitness function. How good is this solution? The best candidates are selected to reproduce, mixing and mutating their genes to create a new generation. Over many iterations, weak solutions die out, strong ones proliferate, and the population as a whole evolves toward optimal answers. This approach shines in problems too complex for direct computation. From designing circuits to optimizing logistics routes, GAs explore vast search spaces by balancing randomness with selection. Unlike traditional algorithms, they don't require a clear path to the solution, just a way to measure fitness. One striking use is in engineering, where genetic algorithms have designed antennas with bizarre, asymmetrical shapes that outperform human-made designs. In art and music, they evolve patterns or melodies, blending mathematics with creativity. The power of GAs comes from diversity and iteration. By keeping many possibilities alive and letting them compete, the algorithm avoids being trapped in local optima. Just as in nature, variety and mutation spark innovation. Genetic algorithms remind us that problem solving doesn't always follow straight lines. Sometimes, the best way forward is to let evolution do the work, testing, discarding, and improving until something extraordinary emerges. Imagine heating metal until it glows, then cooling it slowly so its atoms settle into a perfect crystalline structure. That process, called annealing in metallurgy, inspired a powerful optimization technique, simulated annealing. Instead of metal atoms, it works on solutions, exploring possibilities by adding randomness, then gradually reducing it to settle on an optimal answer. At its core, simulated annealing is about balance. Early in the process, the algorithm allows large, even bad moves, jumping across the solution space in unpredictable ways. This randomness prevents it from getting stuck in local optimal solutions that look good but aren't truly the best. Over time, the temperature decreases, and the algorithm becomes less willing to accept worse moves, focusing on refining the best solution found so far. The elegance lies in its probabilistic acceptance rule. Worst solutions can be accepted with a probability that decreases as the temperature lowers. This mirrors how cooling metal atoms can still vibrate, but less and less, until they lock into stable positions. Simulated annealing has been used in fields ranging from chip design to airline scheduling, where finding the absolute best arrangement is computationally daunting. It's especially useful for problems where brute force search is impossible, yet some randomness can uncover surprising shortcuts. The method reminds us that chaos, if controlled, can be creative. By allowing exploration before narrowing focus, simulated annealing demonstrates that sometimes progress requires detours, mistakes, and risk-taking. It's a strategy, not just for algorithms, but for life. Move broadly at first, explore boldly, then refine carefully until the best solution emerges. Picture a flock of birds weaving across the sky. No single bird controls a group, yet together they form elegant, coordinated patterns. Particle swarm optimization borrows this idea, using swarms of simple agents particles that collaborate to find optimal solutions. Each particle represents a candidate solution, moving through the search space with a velocity influenced by two factors: its own best-known position and the best-known position of the entire swarm. Over time, particles adjust their trajectories, drawn both by personal experience and by collective wisdom. This dual pole creates balance between individual exploration and group convergence. PSO doesn't require gradients, derivatives, or detailed mathematical structure, making it versatile across problems. It has been applied in machine learning, engineering, finance, and robotics. For example, PSO can optimize neural network weights or tune parameters in systems too complex for traditional calculus-based methods. What makes PSO remarkable is its simplicity. With only a few lines of rules, particles exhibit emergent intelligence, collectively converging on good solutions. It's proof that cooperation and information sharing can outperform isolated trial and error. Like birds or fish schools, PSO thrives on diversity. The swarm explores broadly, but as good solutions emerge, particles naturally align, accelerating convergence. This echoes nature's principle. Simple rules plus group dynamics can produce surprisingly intelligent behavior. Particle swarm optimization shows that intelligence doesn't always come from complexity. Sometimes, it emerges from the harmony of many simple agents working together toward a shared goal, an idea as relevant to computation as it is to life itself. Imagine standing in a maze trying to reach the exit. You could wander aimlessly, or you could use a strategy. Always move in the direction that looks closest to your goal while keeping track of the path you've taken. That's the essence of A** search, one of the most famous pathfinding algorithms. A combines two key ideas: the cost of reaching the current position and a heuristic estimate of how far it is to the goal. By balancing these two, it avoids both reckless shortcuts and endless detours. The algorithm prioritizes nodes with the lowest sum of actual cost plus estimated remaining cost, guiding it intelligently toward the target. This blend of precision and intuition makes A widely used in navigation systems, robotics, and video games. Whether you're asking your GPS for the fastest route home or controlling a game character through a virtual world, A is often working behind the scenes. The power of A comes from heuristics. A good heuristics, like straight line distance on the map, helps the algorithm find optimal paths quickly. A poor one can slow it down, but as long as the heuristic never overestimates, A guarantees an optimal solution. A represents more than just pathfinding. It's a model of problem solving, weighing the cost of what you've done with an estimate of what remains. It captures the human intuition of balancing experience with foresight. Every journey, whether across maps, mazes, or life, benefits from A's philosophy. Progress is fastest when you consider both where you've been and where you are going. Imagine walking into a crowded room where everyone speaks at once. You can't separate each voice. But with time, you start to detect patterns. This voice belongs to one person, that one to another. Expectation maximization does something similar. It finds hidden structures in data when direct observation isn't possible. The EM algorithm works in two alternating steps. First, the expectation step estimates hidden variables based on current parameters. Then, the maximization step updates the parameters to best fit those estimates. By repeating this cycle, the algorithm gradually converges toward a solution. One classic application is Gaussian mixture models, where data points may belong to multiple overlapping distributions. EM helps untangle them, estimating means, variances, and probabilities of membership. It's like a mixing voices in the noisy room, gradually sharpening the picture of who's speaking. Beyond statistics, EM is used in genetics, speech recognition, and computer vision. Anywhere incomplete or uncertain data must be modeled. Its genius lies in handling ambiguity, not by solving it outright, but by iteratively refining guesses until clarity emerges. The method mirrors human reasoning. When faced with uncertainty, we make our best guess, then adjust as new evidence comes in. EM formalizes this intuition into a structured algorithm. Expectation maximization reminds us that progress often comes not in one leap, but through cycles of guessing, refining, and improving. Even in the noisiest environments, hidden patterns can be revealed if we're patient enough to keep alternating between expectation and adjustment. Imagine you're running a massive library, but you don't have the space to keep detailed records of every book. Instead, you design a clever system, a compact checklist that can quickly tell you whether a book is definitely not in the library, or maybe it is. That's the magic of Bloom filters' probabilistic data structures designed to test membership efficiently. A Bloom filter is built from a simple bit array and a set of hash functions. When an item is added, it's hashed multiple times, and the corresponding bits in the array are set to 1. To check membership, the algorithm hashes the query and inspects the same positions. If any bit is 0, the item is definitely not present. If all are 1, the item may be present, though with a chance of a false positive. This trade-off, no false negatives, but possible false positives, makes Bloom filters incredibly space efficient. They're perfect for large-scale systems where exact storage is impractical. Bloom filters are widely used in networking, search engines, and databases. For example, they help Google Chrome quickly check if a website is potentially malicious without downloading an entire blacklist. In distributed databases like Cassandra, they prevent unnecessary disk lookups, saving time and resources. The elegance of Bloom filters lies in embracing imperfection. By allowing a small margin of error, they achieve speed and scalability that exact methods can't match. It's a reminder that sometimes certainty is less important than efficiency. In the world of limited memory and overwhelming data, Bloom filters prove that maybe can be good enough. Picture a chessboard. Every move you make has consequences, and your opponent is always trying to counter you. The Minimax algorithm captures this struggle. It's a method of making decisions by minimizing the possible maximum loss. In other words, assume your opponent plays perfectly and choose the move that leaves you with the best outcome in the worst case. The algorithm works by exploring possible moves in a game tree, alternating between maximizing and minimizing layers. At the maximizing level, you assume it's your turn and try to improve your position. At the minimizing level, you assume your opponent responds optimally to weaken your position. By evaluating outcomes recursively, Minimax identifies the most robust strategy. To make this feasible, heuristics and pruning techniques are applied. Alpha-beta pruning, for example, cuts off branches of the game tree that cannot affect the final decision, dramatically speeding up search. Without pruning, Minimax would collapse under the sheer number of possibilities. This method underpins computer game playing AI, from classic chess engines to modern turn-based strategy bots. It reflects not only cold computation, but also the essence of human strategy. Think ahead, anticipate the worst, and prepare accordingly. Minimax is more than a chess tool. It models real-world decision-making in negotiation, economics, and security. The core idea is universal. When faced with uncertainty and opposition, the safest path is to plan for the toughest adversary. In life, as in games, Minimax reminds us that strong strategies come not from wishful thinking, but from preparing for the harshest possible counterplay. Imagine sending a letter across enemy territory. You lock it in a box, but the person on the other side has the only key to open it. How can this be possible when you never exchange keys beforehand? That's the magic of RSA encryption, one of the most widely used methods for securing communication in the digital age. RSA is built on the mathematical difficulty of factoring large numbers. It starts with two huge prime numbers, multiplied to create a composite. While multiplying primes is easy, reversing the process, finding the original primes from the product is nearly impossible for large enough numbers. This asymmetry creates the foundation for security. The algorithm uses two keys, a public key for encryption and a private key for decryption. You can share the public key with the world, anyone can lock a message for you, but only you can unlock it with your private key. This solves the problem of secure communication between strangers, making everything from online banking to private messaging possible. RSA's power lies not in secrecy, but in openness. The public key can be broadcast freely, while the private key remains guarded. Even if millions know the public key, the underlying math ensures the private key cannot be derived. The elegance of RSA is that trust emerges from impossibility. As long as factoring large numbers remains computationally infeasible, RSA provides a shield against prying eyes. Every time you browse securely, shop online, or send a private email, RSA may be working silently in the background, turning prime numbers into guardians of trust. Picture two people shouting numbers across a crowded room while enemies listen. By the end of their exchange, they somehow share a secret code that no eavesdropper can reconstruct. This is the brilliance of the Diffie-Hellman key exchange, a protocol that allows two parties to establish a shared secret over an insecure channel. The method uses modular arithmetic and the difficulty of the discrete logarithm problem. Each participant selects a private number, then combines it with a public base to generate a partial key. They exchange these partial keys openly. Then, by combining their private secret with the other person's partial key, both compute the same shared value, a common secret known only to them. To outsiders, the numbers exchanged look ordinary. But without knowing the private numbers, reconstructing the secret is nearly impossible. This is why Diffie-Hellman revolutionized cryptography. It proved secure communication could be established without prior trust. The protocol is often paired with other encryption schemes to create robust security. Forming the backbone of many modern systems like TLS, the technology behind HTTPS, what makes Diffie-Hellman so elegant is its paradox, a secret born from openness. By leveraging hard math problems, two strangers can safely whisper in a crowd. Every time you see the padlock icon in your browser, Diffie-Hellman may be at work, ensuring your connection is secure even when the entire world is listening. Imagine trying to teach a child how to throw a ball. They throw, miss the target, and you gently guide them a little higher, a little softer. With each correction, they improve. Backpropagation works the same way, but for machines. It's the algorithm that trains neural networks, powering modern AI. At its core, backpropagation is about error correction. A neural network makes a prediction, compares it to the true answer, and measures the difference called loss. Then, using calculus, the algorithm computes how much each connection in the network contributed to the error. By nudging the weights slightly in the right direction, the network improves over time. This process repeats millions of times, with tiny adjustments accumulating into remarkable accuracy. From recognizing faces to translating languages, backpropagation allows machines to learn complex patterns that no programmer could hand-code directly. The brilliance of backpropagation lies in its efficiency. Instead of blindly guessing how to adjust, it uses gradients mathematical slopes to make targeted changes. This is like climbing down a mountain by following the steepest descent until you reach the valley of minimum error. It also mirrors human learning. Mistakes are signals, not failures. Each wrong guess becomes feedback that shapes the next attempt. Backpropagation transformed artificial intelligence from a dream into a reality. Every time you interact with voice assistants, recommendation engines, or image recognition apps, backpropagation is quietly at work, turning errors into intelligence. Imagine solving a problem not by designing a perfect solution, but by letting nature do the work. Genetic algorithms take inspiration from evolution. using survival of the fittest to generate solutions over time. The process begins with a population of candidate answers, represented as strings of data. Each is evaluated with a fitness function to measure how good it is. The best candidates are selected to reproduce, combining their traits in crossover operations. Occasionally, mutations introduce random changes, adding diversity. Over generations, the population evolves toward better solutions. This method is powerful for problems with enormous search spaces where traditional methods fail. From optimizing flight schedules to designing antennas for NASA, genetic algorithms discover solutions no human could easily craft. What makes them fascinating is their unpredictability. Just like natural evolution, they don't guarantee the best solution, but often uncover surprising and creative ones. Genetic algorithms remind us that trial and error combined with variation and selection can achieve brilliance. Instead of rigid planning, they thrive on randomness guided by fitness. Every time you hear of AI discovering something unexpected, a new design, a novel strategy, it may be evolution at work in silicon, echoing the same principles that shaped life itself. Imagine trying to predict the future of a storm. The exact path of every gust of wind is impossible to calculate. But if you simulate thousands of random possibilities, patterns emerge. This is the essence of Monte Carlo simulations, harnessing randomness to understand uncertainty. The algorithm works by running many random trials of a process and observing the outcomes. Instead of trying to solve a problem with exact equations, it uses probability to approximate answers. The more simulations you run, the more accurate the picture becomes. Monte Carlo methods are used in finance to estimate risks, in physics to model particle behavior, and in engineering to test reliability under uncertainty. They're invaluable when a system is too complex for deterministic solutions. For example, predicting stock market fluctuations is notoriously difficult. But by simulating thousands of potential scenarios based on random variables, Monte Carlo provides a range of likely outcomes. In medicine, it helps forecast the spread of diseases, showing not one future, but many possible ones. The beauty of Monte Carlo is its humility. Instead of claiming certainty, it embraces randomness, showing that probability can be more useful than prediction. Life itself is uncertain, and Monte Carlo reminds us that acknowledging chaos can lead to deeper understanding. It's not about predicting exactly what will happen, it's about preparing for what could happen. Picture your brain trying to remember everything you've ever seen. Impossible, right? At some point, you have to forget less useful memories to make space for new ones. Computers face the same challenge with memory, and page replacement algorithms decide what stays and what goes. When programs demand more memory than is physically available, operating systems use virtual memory. Data is stored in pages, and when memory runs out, some pages must be swapped to disk. But which ones? That's the job of page replacement. Algorithms like least recently used, LRU, assume that data not accessed recently is less likely to be needed again. FIFO first in first out simply removes the oldest page. More advanced methods predict future access patterns, aiming for optimal performance. These decisions are critical. A bad choice can cause thrashing, where the system spends more time swapping than working. A smart choice keeps the system running smoothly, balancing speed and efficiency. Page replacement is a quiet but essential algorithm, shaping every interaction you have with a computer. Each time you open a new tab, run a program, or load a file, the system is deciding what to keep in its short-term memory and what to let go. It mirrors human memory, selective, sometimes flawed, but necessary for survival in a world of limited space. Imagine navigating a city where roads can suddenly change length, sometimes shorter, sometimes longer, and occasionally even negative, as if a shortcut opened. How would you find the safest route? That's where the Bellman-Ford algorithm comes in. Unlike simpler methods such as Dijkstra's, Bellman-Ford can handle graphs with negative edge weights, making it more versatile when costs can vary. The algorithm works by gradually relaxing the edges of graph. At each step, it checks whether traveling along a certain road improves the known distance to a destination. By repeating this process across all edges, it slowly uncovers the shortest path. After enough iterations, the optimal distances emerge or, in some cases, The algorithm reveals a negative cycle, an endless loop where costs decrease forever. This ability to detect negative cycles is a key strength. In real-world terms, it's like realizing a road system contains an impossible paradox. Driving in circles somehow makes travel cheaper. Bellman Ford doesn't just find routes. It exposes flaws in the system. The algorithm is slower than Dijkstra's but more general. It's applied in fields like computer networking, where routing decisions must adapt to changing conditions, and in economics, where values can sometimes dip below zero. Bellman Ford shows that sometimes progress isn't about rushing to the fastest answer. It's about patience checking again and again until clarity emerges and being aware when a problem has no stable solution at all. Imagine a city of pipes carrying water. Each pipe has a capacity, and your goal is to push as much water as possible from the source to the destination. Some pipes bottleneck the system, limiting the total flow. How do you calculate the maximum flow? That's the problem solved by the Ford-Fulkerson algorithm. It works by searching for a path through the network that can still carry extra flow. These are called augmenting paths. Each time one is found, the algorithm pushes as much flow as possible along it, then updates the network to reflect the new usage. Step by step, it squeezes every possible unit of flow through the system until no more augmenting paths remain. The result is the maximum flow, the greatest amount of material that can move through the network without breaking capacity limits. This has countless applications: managing traffic through roads, maximizing data transfer in networks, or even matching applicants to jobs in bipartite graphs. What makes Ford-Fulkerson fascinating is its adaptability. The algorithm doesn't try to calculate everything in one leap. It incrementally improves the solution until nothing more can be added. In many ways, it mirrors problem solving in life. We often can't achieve perfection in a single attempt. Instead, progress comes from finding what still works, pushing it further, and gradually reaching the limit of possibility. Imagine you're running a massive library and someone asks, "Have we seen this book before?" Storing every title exactly would take endless space. But what if you could answer probably yes or definitely no with just a tiny bit of memory? That's the power of a Bloom filter. A Bloom filter is a space-efficient probabilistic data structure. Instead of keeping full records, it uses multiple hash functions to map an item into a fixed-size array of bits. When you add something, its hash values flip certain bits to 1. When you check membership, the filter looks at those bits. If any are 0, the item is definitely not in the set. If all are 1, the item is probably in the set, though there's a chance of a false positive. This trade-off is intentional. Bloom filters save enormous amounts of memory while tolerating occasional uncertainty. They're used by web browsers to quickly check whether a URL is malicious, by databases to filter queries before expensive lookups, and by large-scale systems like Google's Bigtable to keep storage efficient. What makes Bloom filters fascinating is their embrace of imperfection. They don't aim for certainty, but for practicality, compressing knowledge into something small and fast. In life, as in computing, sometimes probably is good enough, especially when resources are limited. Bloom filters remind us that memory itself can be optimized. We don't need to recall everything exactly to make smart decisions. Imagine running a huge website with millions of users. Their data needs to be spread evenly across multiple servers. But what happens when one server fails or when you add a new one? Moving all the data would be chaos. This is where consistent hashing saves the day. Consistent hashing distributes data across servers in a way that minimizes reorganization when servers join or leave. Instead of mapping items directly to servers, both items and servers are placed on a hash ring using a hash function. Each item is stored on the first server clockwise from its position. When a server is added or removed, only a small fraction of items need to move, keeping the system stable and efficient. This approach is the backbone of modern distributed systems, from content delivery networks to massive databases. It allows companies like Amazon, Netflix, and Facebook to handle unpredictable traffic and server failures without grinding to a halt. The brilliance of consistent hashing is its elegance. A simple idea placing nodes and data on a virtual circle solves one of the hardest challenges of scaling systems: how to spread the load fairly while minimizing disruption. In many ways, it mirrors balancing life. When change happens, a system that can adapt smoothly without total upheaval is the one that thrives. Imagine a team working on a shared document. Everyone must agree on what the current version looks like, but what if one person goes offline or another starts making conflicting changes? Chaos would follow. Distributed computer systems face the same challenge, and Raft is an algorithm designed to keep everyone in sync, even when failures occur. Raft works by electing a leader among a group of servers. This leader receives all updates and distributes them to followers. If the leader fails, a new one is elected quickly, ensuring the group always has someone coordinating the process. Through this simple structure, Raft maintains a consistent log across all servers, guaranteeing that everyone sees the same sequence of events. The genius of Raft lies in its clarity. While earlier consensus algorithms like Paxos were notoriously difficult to understand, Raft was designed for readability. Its steps, leader election, lock replication, and safety are intuitive yet powerful enough to power real-world systems like Kubernetes and XRD. What Raft demonstrates is that trust in distributed systems comes not from perfection but from redundancy. Failures are expected, but the algorithm ensures that recovery is fast and agreement is preserved. In a way, Raft reflects human organizations. Strong leadership, smooth transitions, and clear rules can keep a group moving forward even in times of uncertainty. Every time you send a secure message, buy something online, or log into your bank, cryptography is protecting you. Modern encryption depends on one assumption. Factoring huge numbers into primes is nearly impossible for classical computers. Shor's algorithm, however, threatens to overturn that foundation. Developed in the 1990s by mathematician Peter Shor, this quantum algorithm can factor large numbers exponentially faster than any classical method. On a traditional computer, factoring a 2048-bit number would take longer than the age of the universe. With Shor's algorithm running on a powerful enough quantum computer, it could be cracked in hours or even minutes. The implications are staggering. RSA encryption, which underpins much of the internet's security, would collapse. Digital signatures, secure communication, and financial transactions would suddenly be vulnerable. Governments and companies around the world are already preparing for this possibility, researching post-quantum cryptography to stay ahead. But Shor's algorithm is more than a threat. It's also a beacon showing the extraordinary potential of quantum computing. By harnessing superposition and interference, it solves a problem once thought unbreakable. It demonstrates that our mathematical limits are not fixed, but can be expanded with new paradigms of computation. In essence, Shor's algorithm is both a sword and a mirror. A sword that could shatter digital security, and a mirror reflecting how fragile even our strongest protections can be in the face of new ideas. Imagine mailing a letter in a locked box. You don't have the key, but you can still close the box and send it safely. Only the person with a private key can open it. That's the idea behind RSA, the algorithm that secures much of the world's online communication. RSA is based on a simple yet profound principle. Multiplying two large prime numbers is easy, but factoring their product is extremely hard. A public key, shared openly, is generated from these primes, while the private key is kept secret. Messages encrypted with the public key can only be unlocked by the corresponding private key. This balance between openness and secrecy allows strangers to exchange information securely. Whether logging into a website, sending an email, or processing a bank transaction, RSA is working silently in the background. What makes RSA extraordinary is its longevity. Created in the 1970s, it remains one of the most widely used encryption methods. Yet, it also carries a ticking clock. Algorithms like Shor's suggest that one day quantum computers could break RSA's foundation. Until then, RSA embodies resilience, an elegant system that has guarded digital trust for decades. In many ways, RSA represents a paradox. It relies on a problem that seems impossible to solve, and yet its eventual breaking is inevitable. For now, though, it continues to be the lockbox of the digital age. Imagine whispering a secret in a crowded room without anyone else hearing it. How could two people, surrounded by listeners, create a shared key for communication? The Diffie-Hellman key exchange answers this puzzle. At its core, Diffie-Hellman allows two parties to generate a shared secret over an insecure channel. Each begins with a private number and exchanges public information derived from it. Using modular arithmetic, both can independently arrive at the same secret key, while eavesdroppers are left with useless fragments. The brilliance of this method is that no secret is ever transmitted. Even if spies capture every message, they cannot reconstruct the shared key without solving an intractable mathematical problem, the discrete logarithm. This breakthrough, developed in the 1970s, laid the foundation for modern cryptography. Every time you see the padlock symbol in your browser, signaling a secure HTTPS connection, you're witnessing a descendant of this idea at work. What's fascinating about Diffie-Hellman is its blend of openness and intimacy. By exchanging information in public, it creates privacy. By revealing certain numbers, it hides the true secret. It's a paradoxical dance of mathematics, turning exposure into protection. In life, too, sometimes trust is built not by hiding, but by sharing just enough to prove we're safe. Imagine needing to prove you know the password to a secret room, but you don't want to say the password aloud. Is it possible to convince someone you know it without ever revealing it? Zero-knowledge proofs are the mind-bending solution to this puzzle. A zero-knowledge proof allows one party, the prover, to convince another, the verifier, that a statement is true without revealing any details beyond the fact of its truth. For example, you could prove you know the solution to a puzzle without actually showing the solution itself. This is achieved through clever sequences of challenges and responses that would be impossible to fake consistently without actually possessing the knowledge. The implications are enormous. Zero-knowledge proofs underpin privacy-preserving cryptocurrencies like Zcash, where transactions can be verified without exposing sender, receiver, or amount. They also have applications in authentication systems, letting you prove your identity without handing over sensitive data like a password or biometric scan. The magic lies in the paradox. Knowledge is demonstrated without being transferred. It challenges our usual notion that proof requires exposure. Instead, zero-knowledge proofs create a world where trust can be established without giving away secrets. In a broader sense, they reflect how trust can function in human relationships too. Sometimes we don't need all the details, just enough certainty to believe. Imagine a group of generals planning an attack. Some may be traitors trying to sabotage the plan. The loyal generals need to agree on a single strategy, but how can they coordinate if some of their messages are false? This is the Byzantine general's problem, and Byzantine fault tolerance, BFT, is the algorithmic solution. BFT ensures that even if some participants in a distributed system act maliciously or send conflicting messages, the honest majority can still reach consensus. By using multiple rounds of communication and majority voting, the system filters out bad actors and prevents catastrophic failure. This resilience is crucial in blockchain technology, where not every participant can be trusted. Cryptocurrencies like Bitcoin and Ethereum rely on variations of BFT to maintain a consistent ledger of transactions despite potential attackers. Similarly, aerospace systems and nuclear control software use BFT to remain reliable even in the face of hardware faults or deliberate sabotage. The brilliance of Byzantine fault tolerance is its assumption that dishonesty is inevitable. Instead of demanding perfect honesty, it builds trust out of mistrust, ensuring stability in hostile conditions. In a way, it mirrors society itself. We thrive not because everyone is honest, but because we design systems that can endure dishonesty without collapsing. Imagine you're reading a book, and based on the current word, you try to guess what comes next. If the word is peanut, there's a high chance the next is butter. That's the essence of Markov chains, predicting future events based only on the present state, without needing the entire history. A Markov chain is a mathematical model where each step depends solely on the current position. Think of weather forecasting. If today is sunny, the probability of tomorrow being sunny might be 70%, cloudy 20%, and rainy 10%. Each day unfolds based on these probabilities, creating a chain of linked events. This simplicity is surprisingly powerful. Markov chains underpin text generation, speech recognition, game AI, and even Google's PageRank. They model customer behavior in stores, disease spread in populations, and patterns in financial markets. Wherever uncertainty exists, Markov chains offer a framework for prediction. What makes them fascinating is a balance between randomness and structure. They reveal hidden order within apparent chaos, showing how the present quietly shapes the future. Even though they never look back, they manage to capture patterns that feel eerily predictive. In a way, Markov chains mirror daily life. We don't carry every past detail with us, but our current state, our mood, our choices, our environment nudges what happens next. The past matters, but often only through the narrow window of the present. Imagine teaching a computer to design the perfect airplane wing. Instead of programming the solution directly, you let it evolve one. That's the idea behind genetic algorithms. Optimization inspired by natural selection. A genetic algorithm begins with a population of random solutions. Each is evaluated for fitness against a goal, like fuel efficiency or structural strength. The best solutions are selected to create offspring, mixing traits and occasionally mutating. Over many generations, the population improves, often producing results more innovative than what humans would design. This method has been used to optimize everything from scheduling airline routes to designing antennas for space missions. In one famous case, NASA's evolved antenna design looked bizarre and counterintuitive, but worked better than any human-engineered alternative. The beauty of genetic algorithms lies in their creativity. By mimicking evolution, they escape rigid human assumptions and explore unexpected possibilities. They're reminders that trial, error, and adaptation can lead to astonishing breakthroughs. In essence, they highlight that problem solving isn't always about direct control. Sometimes the best answers emerge from letting go, setting the conditions, and allowing solutions to grow naturally, just as nature has done for billions of years. Imagine staring at a photo of a cat. You recognize it instantly, even if it's upside down, blurry, or drawn as a cartoon. But how does your brain do that? For decades, scientists struggle to replicate this miracle of perception until they discover artificial neural networks, algorithms, loosely inspired by the billions of neurons in the human brain. A neural network is built from layers of interconnected nodes, or neurons. Each connection has a weight adjusted during training that determines how strongly one neuron influences another. When data passes through the network, these weights transform inputs into outputs, gradually learning to recognize patterns. At first, the network knows nothing. Show it 1,000 images of cats and dogs, and it stumbles. But over time, by comparing its guesses with the correct answers, it tweaks its connections, slowly improving. Eventually, it can detect subtle details, whiskers, paw shapes, ear angles, things it was never explicitly programmed to notice. The impact of neural networks is everywhere. They power voice assistants that recognize your speech, recommendation systems suggesting what to watch, medical scans that spot tumors earlier than doctors, and self-driving cars that navigate chaotic roads. They've even composed music, painted artworks, and written convincing stories. What makes neural networks so fascinating isn't just their utility, it's their unpredictability. Sometimes they discover solutions humans never anticipated. Other times, they fail in bizarre ways, misclassifying a school bus as an ostrich because of a pattern in pixels. They are powerful yet mysterious, mimicking human thought but never fully transparent. In a sense, neural networks remind us of our own mind, capable of brilliance, yet often opaque even to ourselves. If neural networks are the brain, convolutional neural networks or CNNs are the eyes. They are the reason machines can see the world, recognizing faces, objects, and scenes with astonishing accuracy. Traditional neural networks struggle when inputs become too complex. Imagine trying to feed every pixel of a 4K photo into a basic network, it would drown in data. CNNs solve this problem by focusing on small, localized patterns, much like how our visual cortex processes information. The process begins with convolution, sliding small filters across the image to detect edges, curves, and textures. Early layers might identify simple features like lines or corners. Deeper layers combine these into complex structures, eyes, wheels, buildings, until the network can recognize entire objects. Pooling layers further compress the data, ensuring the network captures what matters most while ignoring irrelevant noise. CNNs have transformed technology. They power facial recognition in smartphones, medical imaging systems, detecting early signs of disease, and even Mars rovers analyzing alien landscapes. They are behind every AI-generated artwork, every object detection algorithm in self-driving cars, and every surveillance system scanning crowds in airports. What makes CNNs captivating is their ability to create meaning from raw pixels. A jumble of numbers becomes a coherent picture, just as your eyes and brain turn photons into understanding. And like human vision, CNNs aren't perfect. They can be fooled by tiny distortions invisible to us, raising questions about trust and reliability. Still, their existence is profound. Machines can now see, not because we taught them what a cat or a car looks like, but because we built systems that teach themselves layer by layer to construct vision from fragments. It's not just technology, it's an artificial sense, a new way for machines to experience the world. Have you ever wondered why Netflix seems to know exactly what show you binge next? Or how Spotify suggests songs that feel like they've been pulled from your own mind? Behind these experiences are recommender systems, algorithms quietly shaping our choices every day. At their core, recommender systems try to answer simple but powerful question. Given what we know about you, what else might you like? There are two main approaches. The first is collaborative filtering, which assumes that if two people share similar tastes, they'll likely enjoy the same future items. If you and a stranger both love the same movies, chances are you'll enjoy each other's favorites too. The second is content-based filtering, which looks at the features of items, themselves, genres, actors, rhythms, keywords, and compares them to your past preferences. The magic happens when these methods combine. Think of YouTube. It doesn't just suggest videos similar to what you watched. It also looks at the patterns of millions of other viewers to refine its guesses. Over time, the system learns not only what you enjoy, but when, how long, and in what context you engage. Recommender systems are more than convenience, they influence culture. They decide which books become bestsellers, which songs go viral, which creators rise to fame. They can even trap us in filter bubbles, reinforcing our existing tastes and limiting exposure to new perspectives. What's fascinating is how these algorithms mirror human intuition. Friends often recommend things based on shared taste. Recommender systems do the same, but at a scale no human could achieve. They are the invisible curators of modern life, quietly steering billions of choices every day. Imagine dumping a deck of cards onto a table, face up, completely scrambled. How would you arrange them in order by number, by suit, or both? This simple task of organizing chaos is at the heart of sorting algorithms, some of the oldest and most essential in computer science. Sorting matters because order brings efficiency. Search through a list of 10 unsorted names, and you may need to check each one. But in a sorted list, you can leap directly to where your target should be. Sorting is the silent enabler of fast databases, responsive websites, and smooth user experiences. There are many ways to sort. Bubble sort compares adjacent items, swapping them until the list is ordered simple but slow. Merge sort divides the list into halves, sorts each, then merges them back together efficient and elegant. Quick sort picks a pivot, splits the list around it, and recursively sorts the parts often the fastest in practice. What makes sorting algorithms interesting isn't just performance but philosophy. Some are brute force, tirelessly grinding through comparisons. Others are strategic, dividing and conquering. Each reflects a different way of thinking about order, efficiency, and problem solving. Even in everyday life, we sort constantly: books on shelves, clothes in drawers, files on computers. Algorithms simply formalize this instinct, turning chaos into structure with remarkable speed. They may seem humble compared to flashy AI, but without sorting, the digital world would collapse into disorganized noise. Picture yourself in a giant maze, walls stretching high above your head. You need to reach the exit, but there are countless twists, dead ends, and loops. How do you decide which route to take? Computers face this challenge constantly, whether plotting the fastest path for a delivery van, guiding a robot through a warehouse, or even routing data across the internet. The solution: pathfinding algorithms. One of the most famous is Dijkstra's algorithm, which calculates the shortest route from one point to every other point, step by step, like water flowing outward. Another is A, a more advanced version that doesn't just explore blindly but estimates which paths are most promising, combining logic with intuition. These algorithms don't just find any path, they find the best one, based on criteria like distance, time, or cost. In video games, they decide how enemies chase you across complex terrain. In cities, they power GPS apps, finding the fastest way home through traffic. On a global scale, they manage airline routes, shipping lanes, and even planetary rovers navigating alien landscapes. What's fascinating is how human they seem. When you're lost, you don't check every possible route, you look for clues, shortcuts, landmarks. Pathfinding algorithms mimic that reasoning, balancing exploration with efficiency. And just like us, they sometimes get stuck or take unexpected detours when conditions change. Every journey, digital or physical, owes something to pathfinding. They are the silent guides, turning chaos into direction, helping both people and machines move forward through the complexity of the world. Imagine a world where no one trusts anyone, yet everyone still manages to agree on the truth. That's the paradox solved by blockchain consensus algorithms, the beating heart of cryptocurrencies like Bitcoin and Ethereum. Normally, trust in transactions comes from a central authority, a bank, a notary, a government. But blockchains remove the middleman. Instead, thousands of computers spread across the globe must all agree on the state of a shared ledger, who owns what, who sent money where, and whether each transaction is valid. The challenge: how do strangers who don't know or trust each other agree without a single point of failure? Different consensus methods provide the answer. Proof of work makes participants solve difficult puzzles, ensuring that adding a block to the chain requires real effort and energy. Proof of stake selects validators based on the amount of cryptocurrency they stake, rewarding honesty with profits and punishing dishonesty with losses. Other mechanisms like delegated proof of stake or Byzantine fault tolerance add their own twists, each balancing speed, security, and decentralization. The brilliance of blockchain consensus is that it turns selfishness into cooperation. Participants act in their own interest, but the rules of the system align those interests with honesty. Cheating becomes harder and more costly than playing fair. Consensus algorithms are more than finance. They represent a new way of organizing human trust, distributed, transparent, and resilient. Whether you believe in crypto or not, these algorithms hint at a future where cooperation doesn't need central control, only carefully designed rules and incentives. Imagine you're designing a system that stores data for millions of users across the globe. Some people demand that the system never loses information. Others insist it must always be available, no matter what. Still, others want it to remain consistent, so everyone sees the exact same data at the same time. Sounds reasonable, right? The problem is, according to the CAP theorem, you can't have all three. CAP stands for consistency, availability, and partition tolerance. In distributed systems, you can only fully achieve two at once. If you want strong consistency and availability, your system may collapse during network partitions. If you want consistency and partition tolerance, you may sacrifice availability when things break. If you want availability and partition tolerance, you'll sometimes serve outdated or inconsistent data. This trade-off shapes the digital services we rely on. For example, banking systems lean toward consistency. Your balance must be correct at all times, even if it means delays. Social networks, on the other hand, often choose availability. You might see slightly outdated likes or comments, but the service never goes down. The brilliance of the CAP theorem isn't that it limits us, but that it forces clarity. Every system is a negotiation between speed, reliability, and accuracy. Engineers must decide what matters most for this application. Do users prefer speed even if the data lags? Or do they demand strict correctness even at the cost of convenience? CAP is the invisible referee behind every modern database, reminding us that perfection is impossible, but balance is everything. Every time you zip a file, stream a video, or send a message across a network, compression quietly works in the background. At the heart of many compression techniques lies Huffman coding, a beautifully simple algorithm that squeezes information without losing meaning. The idea is intuitive. Not all pieces of data are equally common. In English text, the letter E appears far more often than Z. Huffman coding assigns shorter binary codes to frequent symbols and longer ones to rare symbols. The result? The overall message becomes smaller, saving space and time. Consider a simple example. If A occurs thousands of times, representing it with just 2 bits instead of 8 creates massive savings. Meanwhile, rare characters can afford to take up longer codes, since they barely affect the total. The algorithm builds a tree of frequencies, ensuring no code is a prefix of another, so decoding remains fast and unambiguous. What makes Huffman coding fascinating is how it reflects efficiency in nature. Languages themselves evolve toward compression. Common words get shortened, speech drops redundant sounds. Huffman formalized this instinct into mathematics, giving us a universal tool for shrinking data. From JPEG images to MP3 audio, from old-school fax machines to modern communication protocols, Huffman coding has silently shaped digital life. It reminds us that elegance often lies in simplicity. A clever rearrangement of symbols can save gigabytes, reduce costs, and make the digital world run smoother. Imagine you're trying to find the shortest path across a map, but some roads have tolls, others give discounts, and a few might even pay you to take them. How do you navigate a system where routes can have both positive and negative values? That's exactly the problem solved by the Bellman-Ford algorithm. Unlike Dijkstra's algorithm, which assumes all costs are non-negative, Bellman-Ford can handle negative weights. It works by gradually relaxing edges, repeatedly checking every possible connection, and updating the shortest known path. With each iteration, the algorithm gets closer to the truth until all paths stabilize. But here's the twist. If costs keep decreasing endlessly, the algorithm detects a negative cycle, a loop that reduces distance forever. In real life, that's like finding a perpetual money-making route, which signals that the system is unstable or broken. This ability to deal with uncertainty makes Bellman-Ford vital in areas like financial arbitrage detection, routing in computer networks, and solving complex optimization problems. It may be slower than other methods, but its resilience makes it indispensable when the terrain is unpredictable. Bellman-Ford captures something profound. Progress doesn't always come in leaps, but in steady refinements. By patiently checking, updating, and correcting, it converges on truth even when the landscape is messy. Sometimes the surest way forward isn't the fastest, but the most persistent. What if computer programs could write themselves, not by human engineers carefully typing instructions, but through the raw power of evolution? That's the vision of genetic programming, a branch of artificial intelligence where algorithms evolve into increasingly effective solutions. It begins with a population of randomly generated programs. Each is tested on a task, perhaps recognizing images, predicting numbers, or solving equations. The most successful survive and are combined or mutated to form a new generation. Over time, the code improves, sometimes in surprising ways that no human would have designed. This method has created circuit designs, trading strategies, and even mathematical proofs. In one famous case, evolved programs solved problems with unconventional weird logic, producing results that worked brilliantly but were nearly impossible for humans to explain. The beauty of genetic programming lies in its creativity. By abandoning strict top-down design, it embraces randomness and trial and error, much like natural evolution. The solutions that emerge are often more efficient, strange, and elegant than anything handcrafted. It also raises deep questions. If programs can evolve without us, who really owns the creativity? The human who sets the process in motion, or the algorithm that discovers answers we couldn't imagine? Genetic programming is a reminder that intelligence doesn't always look like deliberate planning. Sometimes it looks like variation, struggle, and survival, whether in nature or inside a computer. Imagine you are trying to track a plane flying through storm clouds. Radar signals are noisy, instruments shake, and the true position is never clear. Yet, air traffic control must know exactly where it is to keep the sky safe. The tool they rely on is the Kalman filter, an algorithm designed to predict hidden states from uncertain, incomplete, and noisy data. The Kalman filter works like a two-step dance: prediction and correction. First, it predicts the system's next state based on physics or prior data, where the plane should be given its speed and direction. Then, when new measurements arrive, it compares them with the prediction. If the data agrees, confidence grows. If it disagrees, the filter adjusts, weighting results by their reliability. The brilliance lies in how it balances trust between models and observations. This algorithm has been essential in fields where precision meets uncertainty, guiding spacecraft during Apollo missions, stabilizing GPS navigation in smartphones, managing stock market forecasts, and even tracking human motion in virtual reality. Anywhere noisy signals threaten clarity, the Kalman filter steps in as a quiet guardian of truth. But the philosophy runs deeper. Life rarely offers perfect information. Decisions are made in uncertainty, guided by what we expect and what we observe. The Kalman filter embodies this balance, reminding us that progress often comes not from certainty, but from continuously updating beliefs in the face of imperfect evidence. It's more than math. It's a way of seeing the world, filtering chaos into order, one correction at a time. Picture a city planning to connect neighborhoods with power lines. They need to link every house so electricity flows everywhere. But wires are expensive. The challenge is clear: how to connect all nodes with the minimum total cost. That's where the minimum spanning tree algorithm comes in. An MST connects every point in a network while avoiding loops and minimizing total distance or cost. Algorithms like Kruskal's and Prim's search for the most efficient arrangement, adding one connection at a time until the web is complete. The result is a perfectly balanced system: no waste, no redundancy, just the cheapest path to connect everything. The applications reach far beyond power grids. MSTs are used to design computer networks, road systems, and airline routes. They also appear in biology, helping scientists map evolutionary trees of species, or in clustering algorithms that reveal hidden structures in data. What makes MSTs beautiful is their universality. No matter how complex the network, there's always a way to strip it down to its essentials, linking everything with the least possible effort. They remind us that sometimes the smartest solution isn't about adding more, but about removing excess until only the necessary remains. In a world filled with tangled systems, the MST is a quiet teacher of efficiency. It whispers that progress doesn't always require more connections. Sometimes it requires the right ones. And in that simplicity lies elegance, power, and clarity. Imagine you run a massive library of millions of books, and someone asks, "Do you have this title?" Checking the entire catalog would take forever. Instead, you use a Bloom filter, a tiny, lightning-fast data structure that can answer almost instantly. But there's a twist. It never gives a false no, only a possible yes. A Bloom filter works by hashing the item through multiple functions and marking bits in a fixed size array. When you later check for the item, the same hashes are applied. If all relevant bits are marked, the filter says, yes, it might be here. If not, it's definitely absent. This trick allows gigantic sets to be compressed into surprisingly small memory footprints. The trade-off? Occasionally, the filter lies with a false positive. It says an element exists when it doesn't. But for many applications, this is acceptable. Imagine a web browser quickly checking whether a URL is on a malware blacklist. If the Bloom filter says no, you're safe. If it says yes, the system double-checks with a full database. Speed and efficiency win, even with the risk of small errors. Bloom filters power spell checkers, databases, blockchain systems, and distributed caches like Google Bigtable. They act like efficient gatekeepers, catching most cases and leaving detailed checks for later. Beyond computing, they offer a life lesson. Sometimes precision isn't necessary. In a noisy world, quick, good enough answers can save immense time and resources. The Bloom filter whispers that it's okay to make small mistakes, as long as they serve the larger goal of efficiency and progress. It's proof that elegance doesn't always mean perfection. Sometimes it means clever imperfection. Imagine walking into a crowded party where strangers mingle in small groups. Without knowing anyone, you could still guess who belongs together by observing how people cluster, who laughs at the same jokes, who stands close, who shares drinks. This is the intuition behind k-means clustering, one of the most widely used algorithms in machine learning. K-means takes a dataset and tries to divide it into k-groups. It begins by choosing k-random centers. Each data point is assigned to the nearest center, forming clusters. Then the centers are recalculated as the average of their assigned points. The process repeats, shuffling boundaries until the clusters settle into a stable shape. Applications are everywhere, segmenting customers for marketing, grouping similar news articles, compressing images, or even organizing galaxies in astronomy. By reducing complexity into neat groups, k-means helps uncover hidden patterns we couldn't see before. But k-means is not perfect. The algorithm depends on the initial random choice of centers, sometimes leading to different results. It also assumes clusters are spherical and equally sized, an assumption real-world data often violates. Yet, despite its simplicity and flaws, it remains a cornerstone of unsupervised learning. There's a deeper philosophy here. Humans naturally seek patterns, even in chaos. K-means formalizes this instinct into mathematics, showing how order can emerge from randomness through iteration. It teaches that clarity isn't about forcing rigid categories, but about refining boundaries until the structure of reality reveals itself. Like finding friends at a crowded party, it's not about knowing every detail. It's about recognizing the invisible forces that bring people and data together. Imagine you're lost in a giant labyrinth. You want to escape quickly, but blindly wandering could trap you forever. Instead, you need a strategy that balances two things: what you've already traveled and how far you might still need to go. This is the essence of the A algorithm, one of the most elegant solutions to pathfinding. At its heart, A is like a disciplined explorer. It doesn't just look at where you are now, it combines the known cost of reaching a point with a heuristic guess about the remaining distance. This dual vision allows it to prioritize the most promising paths, avoiding dead ends and wasted time. If Dijkstra's algorithm explores every possibility, A acts like a chess player, anticipating the future and choosing wisely. Applications are vast, from guiding GPS systems to finding the fastest driving route, to video games where non-player characters chase or flee in believable ways, to robotics, where machines must navigate unpredictable spaces. Even delivery companies use A variants to optimize logistics and save millions. But beyond computing, A carries a metaphor about life. Decisions are rarely about the present alone. We constantly weigh what's being invested against where we hope to arrive. Too much focus on the past leads to inertia. Too much on the future causes reckless leaps. The balance of both the known and the guessed is what turns choices into wisdom. The brilliance of A is its humility. It admits we don't know everything, but insists on using what we do know to chart the smartest possible course. In mazes, in maps, and in life, it teaches us to move forward with both calculation and imagination. Picture yourself trying to send a book over a telegraph, one symbol at a time. Every extra character costs time and effort. How do you compress language so it takes less space but still carries meaning intact? Enter Huffman coding, a foundational algorithm in data compression. The principle is simple but ingenious. Not all letters or symbols are equally common. In English, E appears far more often than Z. Huffman coding assigns shorter binary codes to frequent symbols and longer ones to rare symbols. The result? Dramatically smaller files with zero loss of information. The algorithm works by building a binary tree of symbols, merging the least frequent ones step by step until a hierarchy emerges. The path to each symbol determines its code length. It's like creating a custom shorthand language tailored exactly to the text at hand. This method underpins countless technologies: zip files, MP3 music, JPEG images, and nearly every form of digital storage or transfer relies on Huffman or its descendants. Without it, the internet would crawl under the weight of uncompressed data. Yet the beauty of Huffman coding isn't just technical. It reflects a deeper truth about efficiency. Focus your resources where they matter most. Spend less effort on the ordinary, more on the rare and significant. It's a principle that transcends computing, echoing in communication, design, and even how we live our lives. Huffman coding shows us that information has rhythm and pattern. By recognizing these rhythms, we can strip away redundancy and reveal clarity. It's a quiet algorithm, but without it, our digital age would be drowning in excess weight. Imagine teaching a computer to solve a problem not by strict instructions, but by letting it evolve solutions over generations. That's the magic of genetic algorithms. Inspired by Darwin's natural selection, they treat possible answers like a population of organisms, each competing to survive. The process begins with random guesses. Each candidate solution is evaluated by a fitness function, a score that measures how good it is. The best ones are chosen to reproduce, mixing and mutating their traits to create new offspring. Over many iterations, weak solutions die out, strong ones thrive, and eventually, a remarkably effective answer emerges. Applications are vast, optimizing airplane wing designs, planning stock portfolios, tuning neural networks, or even generating creative art. In robotics, genetic algorithms evolve walking patterns for machines, producing strange but efficient gaits no human engineer would design. The deeper message is that progress doesn't require perfection at every step. It requires variation, failure, and persistence. Just as nature's messy trial and error produced eyes, wings, and brains, digital evolution creates elegant solutions from chaos. In a way, genetic algorithms remind us that intelligence isn't only about logic, it's about resilience. The world isn't built by flawless blueprints, but by constant adaptation. They echo the philosophy that we don't need to know the final path. We just need to keep evolving, and the path will shape itself. Imagine you own a supermarket. You notice that people who buy bread often also buy butter. Then you discover something stranger. Customers who buy diapers also tend to buy beer. This is the kind of insight the a priori algorithm reveals, uncovering patterns in massive transaction data. A priori works by searching for frequent item sets, groups of products that often appear together. It builds from the ground up, first identifying individual items that are common, then expanding into pairs, triples, and beyond. At each step, it prunes combinations that are too rare, focusing only on strong associations. The results can be surprising and powerful. Retailers use it to design promotions, recommend products, and rearrange store layouts. Online platforms use similar techniques for customers also bought suggestions. Even in medicine, a priori helps identify correlations between symptoms and treatments. Philosophically, a priori speaks to the hidden connections that shape our lives. We think we make independent choices, but in reality, behaviors cluster in patterns. Our habits, preferences, and decisions form invisible webs that algorithms can illuminate. But a priori also warns us patterns don't equal causation. Just because two things occur together doesn't mean one causes the other. Still, the algorithm highlights the threads of association weaving through human activity. In essence, a priori is about uncovering structure in the everyday chaos, reminding us that even our most ordinary choices leave footprints of order. Imagine you're a traveler moving through a landscape where not every road is safe. Some paths cost time, others money, and some might even give you resources instead of taking them away. This is the challenge the Bellman-Ford algorithm was built for, finding the shortest path in a graph, even when edges have negative weights. Unlike Dijkstra, which assumes cost can be negative, Bellman-Ford embraces uncertainty. It repeatedly relaxes every edge, updating estimates of the shortest path. With each pass, the map grows clearer, until finally the algorithm converges on the true solution, unless it detects something stranger, a negative cycle, where you can loop infinitely and keep gaining resources. In that case, there is no shortest path at all, only endless exploitation. This algorithm has real-world weight. It helps routing in networks where connections fluctuate, financial models where debt and profit interact, and logistics systems with trade-offs that aren't always positive. It's slower than other algorithms, but its ability to handle negative conditions makes it invaluable. Metaphorically, Bellman-Ford mirrors life. Not all journeys are straightforward. Not all steps cost the same. Sometimes, progress includes setbacks or even opportunities that feel too good to be true, like negative cycles that promise infinite gain but trap you forever. The algorithm's wisdom is in vigilance. It not only finds a path, but warns when the system itself is unstable. Bellman-Ford is a lesson in realism. The world isn't just about clean, positive progress. It's messy, filled with losses, false shortcuts, and dangerous loops. Yet, with persistence and careful recalculation, even in the darkest graphs, direction emerges. 90. Decision trees, the forest of choices. Think of every choice you've made today. Coffee or tea, walk or drive, work or rest. Now imagine writing those decisions down as a branching diagram, where each fork leads to a new possibility. That's the essence of a decision tree, a model that turns uncertainty into structure by splitting complex problems into simple yes-no questions. At its root, the tree starts with a single question, the most informative one. From there, it divides into branches, each representing a possible outcome. Step by step, the tree grows, partitioning data until the leaves represent clear, final answers. The beauty is its interpretability. You can see exactly why the model made a decision. Decision trees power countless real-world systems. Banks use them to evaluate loan risks. Doctors use them to diagnose patients. And online platforms use them to recommend movies or ads. In ensemble methods like random forests or gradient boosting, forests of trees combine for incredible predictive accuracy, becoming some of the most powerful tools in machine learning. But beyond technology, the metaphor is striking. Our lives are forests of branching decisions. Every choice cuts off certain futures while opening others. The tree teaches us that even complex decisions can be broken down into simpler questions, though we must beware of overfitting, seeing patterns that don't really exist. Decision trees show that clarity emerges when we face uncertainty step by step, branch by branch. And while no tree predicts the future perfectly, it gives us a framework to navigate the forest of possibilities. Take any word, sentence, or even an entire book and feed it into a hash function. Out comes a short string of characters, seemingly random, yet perfectly deterministic. Change just one letter, and the hash completely transforms. This is the strange beauty of hash functions, the silent workhorses of the digital world. Hashes compress vast complexity into fixed fingerprints. They secure passwords, ensure files aren't tampered with, and make blockchain possible. When you download a program and verify its checksum, you're trusting a hash to prove authenticity. When cryptocurrencies store transactions, they chain blocks together using hashes, ensuring the past cannot be rewritten. Technically, a hash maps data to a fixed size output. The rules are designed so that collisions two different inputs producing the same hash are astronomically rare. Good hash functions are fast, unpredictable, and irreversible. You can go from input to output, but never backward. Philosophically, hashes represent a paradox. They destroy information while preserving identity. They forget almost everything, yet remember just enough to guarantee uniqueness. It's a reminder that identity in the digital age isn't about depth. It's about a compact summary, a fingerprint that stands for the whole. In life, we too are often judged by hashes, labels, impressions, statistics that reduce our complexity to a few symbols. It's both powerful and dangerous. Just as hashes make systems efficient, they also hide the richness behind the data. A hash is proof that order can emerge from chaos, but also a warning of what gets lost when we compress reality into something smaller. Every day, you stream videos, send texts, and read files, yet rarely think about how that data shrinks to fit through the narrow pipes of the internet. At the heart of compression lies Huffman coding, a clever algorithm that reduces redundancy by assigning shorter codes to common symbols and longer codes to rare ones. Imagine you're encoding English text. Letters like E and T appear often, so Huffman gives them short binary codes like 10 or 1. Rare letters like Z or Q get longer codes. maybe 110,000, 101. When combined, the average message length shrinks dramatically without losing a single detail. This principle drives zip files, JPEG images, MP3 music, and countless other formats. Wherever you see compressed data, chances are Huffman is quietly at work. It's efficient, elegant, and lossless. Nothing is discarded, only represented more wisely. But beyond mathematics, Huffman coding is a philosophy of communication. It teaches that not all messages are equal. Some deserve brevity, others can afford length. It reflects how humans naturally speak. We abbreviate common ideas, but linger on rare ones. In a sense, Huffman is a mathematics of attention. There's a beauty in this balance. By embracing probability, Huffman coding reveals a deeper truth. Information has structure. Nothing is truly random if you know where to look. Even the chaos of language hides patterns that can be compressed, like secrets waiting to be revealed. Every efficient stream of data, every song or film you watch online, owes something to Huffman's insight. It's not just compression, it's the hidden poetry of information itself. Picture yourself standing on the slope of a vast, foggy mountain. You want to reach the lowest valley, but you can't see the entire landscape, only the ground beneath your feet. The strategy? Take a step downhill, then another, then another. This is the essence of gradient descent, the algorithm that powers most of modern machine learning. At its heart, gradient descent is simple. It finds the minimum of a function by moving in the direction where the stiff methods adjust the step size. Each innovation helps models escape traps and converge more efficiently. The metaphor extends far beyond mathematics. In life, we rarely see the full map. We stumble forward, guided only by local feedback, what feels like progress, what doesn't. Sometimes we rush and overshoot, sometimes we inch along too cautiously. Yet, with patience and iteration, downhill becomes a journey of learning. Gradient descent is proof that progress isn't about leaps, but about thousands of small, careful steps. And just like in the fog, the secret isn't knowing the whole terrain, it's trusting that moving a little closer to better will eventually lead to best. Imagine a traveler trying to cross a complex maze. Left or right, forward or back. Countless paths unfold, and brute force exploration would take forever. The genius of search lies in its balance. It doesn't just wander blindly, nor does it rely only on optimism. Instead, it combines the actual cost so far with an estimate of the cost to go, the perfect blend of reality and hope. At each step, A evaluates possible moves with a formula, NGN plus HN, where GN is the true cost traveled, and H is the heuristic estimate to the goal. This balance allows A to prioritize the most promising paths while discarding dead ends. The result? It finds the shortest route efficiently, whether in maps, games, or robotics. If you've ever used GPS navigation, you've relied on A. Behind the scenes, it weighs distances, traffic, and turns, producing not just any route, but the best route within reason. Video games use it to guide characters across digital worlds. Robots use it to navigate real ones. Yet A is more than computation, it's philosophy. It teaches us that decisions should blend experience and foresight. Too much focus on the past, G traps you in what's already spent. Too much focus on the future, H leaves you chasing dreams with no grounding. Wisdom lies in combining both. Every path in life involves a trade-off. Effort already invested and the vision of where you want to go. A shows that the smartest route isn't just the fastest or cheapest. It's the one where the balance of reality and imagination gets you to your destination. Open any book, transcript, or a collection of tweets and count how often each word appears. The most common word will occur about twice as often as the second most common, 3 times as often as the third, and so on. This eerie regularity is called Zipf's law, and it shapes not just language, but music, city sizes, wealth distribution, and even the internet. In English, the dominates. In Spanish, the. No matter the language, the frequency of words follows the same power law curve. Rare words exist, but they taper off with uncanny predictability. It's as if human expression, despite its creativity, is bound by invisible statistical chains. This principle is used everywhere. Search engines optimize rankings based on word frequencies. Natural language processing models compress meaning by prioritizing common tokens, and linguists study how language evolves by watching shifts in these distributions. Even your phone's predictive keyboard leans on Zip-like patterns to guess your next word. But Zipf's law stretches beyond language. City populations follow it. New York towers over Los Angeles, which towers over Chicago. Wealth too. A few billionaires, many millionaires, countless workers. Even website traffic reflects it. A handful of sites dominate the internet, while most linger in obscurity. Why does this happen? Some argue its efficiency language naturally evolves to balance effort and clarity. Others see it as a property of complex, self-organizing systems. But philosophically, Zipf's law is unsettling. It whispers that what feels like freedom, our choice of words, where we live, how we interact, may be governed by mathematical inevitability. Every time you speak or type, you're unconsciously obeying Zipf. Hidden within your words is a universal order, a strange reminder that chaos is never entirely free from structure. What if problem solving could mimic nature itself? Instead of designing the perfect solution, let random variation and survival of the fittest do the work. That's the idea behind genetic algorithms, a class of optimization techniques inspired by Darwinian evolution. The process begins with a population of candidate solutions. Each is evaluated with a fitness function, how well it solves the task. The best are selected, combined, and mutated to produce the next generation. Over time, weak solutions die out, strong ones survive, and entirely new strategies emerge. The algorithm doesn't plan, it evolves. Genetic algorithms have been used to design antennas for NASA spacecraft, schedule airline flights, optimize stock portfolios, and even generate art. Their power lies in adaptability. Instead of rigid logic, they thrive in vast, uncertain search spaces where trial and error beats meticulous planning. But beneath the math lies something deeper, a philosophy of growth. Genetic algorithms mirror life itself, messy, wasteful, yet astonishingly effective. They remind us that progress is rarely linear. Evolution stumbles, explores dead ends, and still uncovers breathtaking solutions. In a way, every human achievement reflects a genetic algorithm of ideas. Cultures mutate, merge, and adapt across generations. Technologies evolve, discarding failures, refining successes. Even personal growth resembles if we try, fail, and learn until we become versions of ourselves better suited to survive. What makes genetic algorithms profound is not just their utility, but their lesson. Perfection doesn't come from control. It emerges from variation, struggle, and resilience. The beauty of evolution, whether biological or computational, is that chaos, given enough time, creates order. Imagine you want to predict the stock market, weather, or even how long it will take to finish a project. The problem: there are too many uncertainties. One wrong assumption can throw off everything. Enter the Monte Carlo simulation, a technique that doesn't try to eliminate uncertainty, but instead embraces it. Here's how it works. Instead of calculating a single best guess, the simulation runs thousands or even millions of random trials. Each trial rolls the dice. Stock returns might go up 5% or down 10%. A storm may or may not arrive. Traffic may be heavy or light. By the end, you don't just have one answer, you have a distribution of possibilities, a map of futures showing what's likely, unlikely, and nearly impossible. Monte Carlo methods are used in finance to value options, in physics to model particles, in engineering to test reliability, and even in video games to simulate randomness. They were named after the famous casino because of their reliance on chance. Yet there's a paradox. Randomness creates predictability. What's striking is the philosophy behind it. Monte Carlo teaches us that the world isn't deterministic, it's probabilistic. Success isn't about certainty, but about understanding the odds. When you cross the street, you're unconsciously running your own Monte Carlo, weighing cars, traffic lights, and timing. Life itself is simulation after simulation. By embracing randomness, we gain clarity. Instead of asking what will happen, Monte Carlo asks what could happen and how often. In a chaotic universe, that's often the closest thing we get to truth. How can you tell if something is in a massive database without storing every single entry? That puzzle is solved by the elegant Bloom filter, a probabilistic data structure that answers a simple yes or no question. Have we seen this before? A Bloom filter doesn't store items directly. Instead, it uses multiple hash functions to mark positions in a compact bit array. When you add something, say an email address or a URL, it flips certain bits. Later, if you check that same item, the filter can quickly confirm if it might be present. The catch? Bloom filters allow false positives. They may say yes when the answer is no, but never false negatives. If it says no, the item definitely isn't there. This trade-off makes them astonishingly efficient. They're used by web browsers to block malicious sites, by databases to speed up lookups, by distributed systems to reduce wasted network calls. They quietly sit behind the curtain of the internet, saving time and memory at enormous scale. Yet, their deeper intrigue lies in the metaphor. A Bloom filter is like human memory. You may think you recognize a face or a song, but sometimes you're wrong. Still, you're rarely mistaken about something completely unfamiliar. It's an algorithm that mirrors how intuition works: fast, lightweight, imperfect, but incredibly useful. Bloom filters remind us that forgetting isn't always weakness. Sometimes efficiency comes not from remembering everything, but from knowing what not to remember. Two suspects are arrested and interrogated separately. Each has a choice: stay silent or betray the other. If both stay silent, they get light sentences. If one betrays while the other stays silent, the betrayer walks free while the silent one suffers a heavy punishment. If both betray, both get moderate sentences. Rational logic says betray, but here's the paradox: the best outcome for both is mutual silence. This is the prisoner's dilemma, the most famous problem in game theory. It captures the tension between individual self-interest and collective benefit. Economists use it to explain why companies compete instead of cooperating, why nations build weapons instead of disarming, and why people sometimes act against the common good. But the dilemma becomes even more fascinating when repeated. In an iterated prisoner's dilemma, choices build reputation. Betray once, and you may pay for it later. Suddenly, strategies like tit for tat, cooperate until betrayed, emerge as surprisingly effective. Trust becomes currency, and long-term relationships outweigh short-term gains. The deeper lesson is unsettling. Rational decision-making doesn't always lead to the best world. Cooperation requires vulnerability, risk, and often defies cold logic. Every friendship, business deal, or treaty is a live experiment of the dilemma. What makes it powerful is its universality. Whether two children sharing toys, corporations setting prices, or countries negotiating peace, the same invisible algorithm applies. The prisoner's dilemma forces us to ask, when should we trust, and when does survival demand betrayal? Pick up a set of financial reports, street addresses, or population data. Now check the first digit of each number. Strangely, 1 appears about 30% of the time, while 9 shows up less than 5%. This uncanny pattern is called Benford's law, and it governs numbers across nature, economics, and even fraud detection. It seems absurd. Shouldn't digits be evenly distributed? But the math reveals otherwise. In many real-world datasets that span several orders of magnitude, lower digits dominate. Earthquake magnitudes, river lengths, electricity bills, all bend to Benford's strange rule. Auditors use it to spot fraud. Fake numbers often fail to follow the law, revealing manipulation. Physicists use it to validate experimental data. Even election analysts use it to flag suspicious results. The law has become a silent detective, catching liars by the shape of their digits. What's fascinating isn't just its utility, but its mystery. Why should reality itself prefer ones over nines? The answer lies in logarithmic scaling. The gap between 1 and 2 feels larger than the gap between 8 and 9 when measuring growth across scales. Nature and human activity unconsciously encode this bias. Philosophically, Benford's law is unsettling. It suggests that hidden beneath randomness is a statistical fingerprint of truth. Numbers carry secrets, And even deception struggles to hide from mathematics. Every time you glance at a dataset, the digits are whispering. And if you know how to listen, they'll tell you whether reality or someone's version of it can be trusted. Every time you stream a video, send a text, or zip a file, you're relying on an idea so simple and elegant it feels almost magical. Huffman coding. At its heart, it's about giving shorter codes to things that appear more often and longer codes to things that appear less. Imagine speaking a language where the takes one tiny sound while rare words like quintessential take long, winding syllables. Suddenly, your sentences shrink without losing meaning. Huffman coding was invented in 1952 by David Huffman, a graduate student faced with a choice: write a term paper or invent something groundbreaking. He chose the latter. His algorithm builds a tree of symbols, assigning the most frequent ones the shortest paths. It's lossless, meaning nothing is thrown away. You can always reconstruct the original message. Why does this matter? Because compression is survival in the digital age. Without it, every photo would be massive, every message bloated, every stream impossible. Huffman's elegant principle quietly powers JPEGs, MP3 second, and countless protocols that move data across the globe. There's also a deeper metaphor here. Human memory itself works like compression. We focus on patterns, repeating themes, shortcuts that make recall efficient. Our brains give short codes to the common and push the rare into long winding archives. Huffman's algorithm isn't just about saving space. It reflects how information and perhaps thought itself can be optimized. In every emoji, every email, every fragment of sound or image zipping across the world, Huffman's tree is working behind the scenes, shaving off waste, turning chaos into order. It's the art of saying more with less. What if problem solving didn't come from logic, but from evolution? That's the radical idea behind genetic algorithms, a class of techniques inspired by Darwin's natural selection. Instead of searching for the perfect solution directly, they breed it. Here's how it works. Start with a population of random guesses. Each guess is tested against the problem, say, designing an antenna, scheduling airline flights, or optimizing a robot's path. The best performing solutions survive while weaker ones fade. The survivors mix and mutate, producing a new generation. Over time, just like in nature, complexity emerges and surprisingly effective solutions evolve. What makes genetic algorithms so powerful is their ability to explore enormous search spaces without getting stuck. Traditional methods can freeze at local optima good but not great answers. Evolution, however, thrives on diversity. A small mutation, a surprising crossover, can unlock entirely new possibilities. They've designed NASA spacecraft antennas, solved complex logistics puzzles, even helped in art and music creation. Watching them work feels less like programming and more like cultivating life inside a computer. Philosophically, they blur the line between human creativity and machine discovery. If an algorithm evolves a masterpiece solution, who is the author, the coder, the machine, or the blind hand of selection itself? Genetic algorithms remind us of a humbling truth. Sometimes intelligence doesn't come from control, but from letting go. By embracing randomness, mutation, and survival, machines mirror the very process that created us. Evolution isn't just history, it's an algorithm, alive inside silicon. Imagine trying to calculate the area of an irregular shape, predict the spread of a disease, or price a company. The idea was born in the 1942 during the Manhattan Project. Physicists like Stanislaw Ulam and John von Neumann faced problems too complex for existing mathematics. Ulam, recovering from illness, passed time playing solitaire and wondered, what if you could estimate the probability of winning by simulating games instead of calculating formulas? This spark led to one of the most important tools in science. Here's how it works. You define a problem space, then simulate random samples within it. The law of large numbers ensures that as the simulations grow, the average converges toward the true answer. To estimate pi, for example, you can randomly throw darts at the square containing a circle. The ratio of hits inside the circle to total throws approximates pi with shocking accuracy. The Monte Carlo method now powers fields as diverse as physics, finance, climate science, and artificial intelligence. Banks use it to model risk, doctors to predict treatment outcomes, and engineers to design safer airplanes. When equations collapse under complexity, Monte Carlo steps in with simplicity. Let's just try it many times and see. What's fascinating is the philosophy hidden inside. We think of science as the pursuit of certainty, yet here is a method built entirely on chance. By embracing randomness, humans uncovered a path to precision. Monte Carlo is not about knowing the future perfectly, but about simulating enough futures that patterns emerge. Every time a weather forecast predicts rain, or a physicist models particles colliding, or a gambler wonders about odds, Monte Carlo is quietly at work, whispering truth through randomness.